All right, so jumping into our next unit, Ohm's law and circuits. Here's a couple things you must know. Because you can't see electricity and because you can't observe it, like water, you can kind of see how it flows, you understand it. Because you can't see that, you have to really know the theory. So everything we're about to talk about is going to be kind of abstract and a little bit scientific, and you're going to kind of be like, well, this isn't really going to help me fix the car, but that's not true. When you get an electrical problem, you have to be able to understand how the electricity works so you can track down the defect. So if a defect is, like I just was talking with a friend the other day who's like, you guys heard of preppers? You know what a prepper is? They prepare for natural disaster. He's all like, you know, he's got off-grid setup and a vehicle to get him out of a zombie apocalypse, and he's got food that could last like a bajillion years, and dry stuff and cooler things. He's got all this type of stuff. Well, this vehicle that's for the zombie apocalypse, he went to jump in it and he goes to start it, it won't start, and all these warning lights come on. And so he's kind of like, I think I know what happened. It sat for a while. He thinks that mice chewed the wires, and he may very well be right, but he doesn't really have the skill set to track down the faults, right? So if you just have your sights and your smell, you pop the hood and you look for clues, but if you don't find the defect, you're kind of done. You're dead in the water. You have no way to diagnose this. Whereas if you really understand electricity, then you can kind of know what to test, right? So if I were to put a meter in your hands right now, you might know some of the basic things I've shown you. How to check voltage, how to check resistance, cool, but you don't really have the knowledge to be able to go after this potential rodent damage, but maybe not rodent damage. It might just be, you know, a wire that got broken. It might be a computer that's gone offline, or an open inside. It could be a number of different things. Right, so you have to understand some of these basics to be able to get to the point where you can do the actual diagnosis. But you'll see as we go through, this is going to be a lot more, you know, hypothetical and theoretical than it is going to be totally practical on the car, okay? So that's why, but the good news is electricity works the same way, and it must always follow the laws of physics. So if you know how it works, it can't act different on this car than it does on that car. It's the same. It's the same on Ford, a Honda, a Toyota. It's all the same. But you have to really know what it says here, the laws. So we're going to cover electricity within the perspective of like Ohm's law and Kirchhoff's law. And like I was saying, you have to know how it works to diagnose it. So kind of a little bit review, but also kind of something new. In Ohm's law, this is what we know. It takes 1 volt to push. Remember, voltage is pressure. So you remember that picture, right? I'm going to show you that picture again. It takes 1 volt to push 1 amp. Remember, 1 amp is the current flow. How many? I forgot how many electrons. A bunch of them. A lot of them. Something million, billion, whatever. Through 1 ohm of resistance. Okay, so that's the formula, and that's how they came up with it. 1 volt will push 1 amp through 1 ohm. Period. So from there, what we could do, we can start to change these. Like if you have 10 volts, that would push 10 amps through 1 ohm. However, because you know the universe has a lot of order, it's pretty impressive. There's things make sense if you understand them. If we had 1 volt and we had 10 ohms of resistance, that would only do 1/10 of an amp, right? So things are proportional. It's not just random. Makes sense? It's almost like, wow, this math makes sense. Even though you may or may not love math, we're going to do a little bit of math. It's not complicated math. It's basically just simple algebra, but if you understand the relationship of the math to the electricity, you'll kind of understand how the electricity works. Make sense? So if the prepper, it's a Jeep Gladiator, it's decked out too. The thing is like, got a lot of money put into it for the zombie apocalypse. If he has, let's say where a mouse chewed something, you know, that's going to add resistance, right? Wouldn't you agree? That's going to add electrical resistance because a lot of the wires are chewed and maybe even corroded and stuff. that would have an effect on the amount of amps going through the circuit. If the ohms go up, the amps are going to go down. Make sense? So in his mind, he could think, oh, the mice chewed a wire in half, it's shorted, but a short circuit would mean less resistance, whereas, that's not really what the case is. See what I'm saying? So you need to really know the theory, know Ohm's law a little bit. If there's added resistance, that means there's going to be less amps. If there's, let's just say, less resistance, that would be more amps. That would be a short. See, so if there's added resistance, don't be talking about shorts. That's more like high resistance or open. Cool? And so we'll cover this Ohm's law quite a bit. We'll even do some practice questions. And then we kind of talked about volts exist when there's a surplus of electrons. So in our battery, for example, there's a surplus of electrons. The truth is that they're on the negative, right? But I'm fibbing with you again. We're going away from that electron theory. There's a surplus on the positive. They're trying to make their way to the negative. The more of a surplus there is on the positive, the higher the voltage is. So when we look at this, if you increase your voltage, that's going to increase your amperage. Cool? But in a car battery, we're typically dealing with, you guys recall, 12.6 would be fully charged. Now if the car is running though, when you start it, the engine's turning, it's turning the belt turns the alternator. The alternator may very well be running 13.5, 13.2, 13.7, so when you start the vehicle, actually your voltage is up a little bit higher. So that would potentially push a little bit more amps through everything, but we'll just call it source voltage from now on. We cool with source voltage? The source voltage may be the 12 point something battery, or it may be the 13 point something vehicle running on the alternator. So, but generally our voltage doesn't change a lot in automotive. If it's discharged, we're still about 12 volts. If it's running, we're still under 14. So you're in a pretty tight range. So we don't put a whole lot of focus on how the voltage changes when we're talking about the source, because it just doesn't change that much. It shouldn't anyway. Cool. And then remember what resistance is? The physical restriction of the conductor. So that's, telling you how hard is it for the electrons to get through. Makes sense? It's the resistance to flow. Cool. And then amps are the number of electrons moved through the conductor. We talked about that. Current flow, that's a volume of electrons moving. And then we talk about this as a summary. If the pressure, volts, stays the same, but the restriction doubles, the amps will be half. Makes sense? It's always proportional. If you double your resistance, you get half the amps. If you half your resistance, you get double the amps. Make sense? It makes sense in math. Cool. All right. Remember this?
Yeah.
So if all of a sudden Mr. Ohm pulls up twice as hard on the rope, amp is going to flow half as much. Make sense? If Ohms relaxes the rope half, amps is going to flow twice as much. Make sense? That's why this is a beautiful visual. And that's mostly what we focus on in automotive. Because like I was saying, the volts generally doesn't change. Typically, volt is pushing about 12 to 14 PSI voltage all the time. That's it. But to be more thorough, just so you understand Ohm's law anyway, what do you think would happen if Ohm stayed the same and volt pushed twice as hard? What would happen to amp?
There'll be
More exactly, more amp, more flow, exactly. So if you visualize this, you probably can understand, right? So Mr. Prepper, if he said, "Oh yeah, a mouse, chewed a wire," that's adding electrical resistance. It would never result in more amp flow. That's like Ohm tightening this even more, right? It'd be reducing it. Okay, cool. Now, if we were to have, let's say the ohms were to go from, let's say in this case, this is 1 ohm. If we were to make it OL, that's a term that I've used once or twice. I'm going to use a lot more. OL means like a full-on open circuit. It means out of limits of the meter. That would be like basically pulled up so hard it completely closed this passage off, blocked it 100%. How many amps are there going to be?
Zero.
Zipperoonie, exactly. So if that mouse chews the wire and now the wire's an open circuit, you already know there's going to be no amps flowing. Basically, let's say that it's for the starter. You know, you turn the car, goes shana na 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 na. If there's an open in the starter circuit and you turn the key, what do you expect is probably going to happen if there's that open? Nothing. It's going to be a no start. And that's what he described. He said he got in, he tried to start it, lights came on, no noise, no nothing. It may very well be that a mouse chewed it, but that would completely sever the passageway and there'd be no electrical flow through there. Whatever the load is not going to work. So used another term right there. The load in the circuit is the thing that does the work. In that case, it was the starter. Now, if the mice chewed the wire to his headlight and it's completely severed, what do you think is going to happen? Exactly, because you have no electrical flow to it. Make sense? So you guys are pretty much understanding the opens. The high resistance is fairly simple. If the mouse chewed it halfway and some corrosion got in there and you just doubled your ohms, that's going to lead half the amps and that headlight is going to be dim. Exactly, right? So we're visualizing it. We're going to keep visualizing it. If that headlight was more like a, let's say maybe a motor, like a power window motor, the motor would move slow. If it was a solenoid, that solenoid wouldn't move with as much force because it wouldn't generate as much of a magnetic field, right? So these things are going to continue to be very related to each other.
So if corrosion happens, would it just be closed? Because that's what.
Okay, I like what you're saying. Corrosion. Let's say the mouse chews it. Right? Why they chew it? Well, actually, some of those wire harnesses are pulled through like a lubricant, and they used to use chemicals. And now they're like, ooh, they should be more environmentally friendly. So they started pulling them through soy-based or peanut oil, by the way, just for your own knowledge. And now the mouse are like, I like this. So they chew it, and then they're like, nah, forget this. I don't like the blue wire. I'm gonna go chew the red wire. If they chew it part way, then right then and there, actually, it might not have really a whole lot of added resistance. But as the moisture sets in and it oxidizes, it corrodes that copper. Now you don't have a clean conductor. That corrosion is an insulator, if you remember the different atoms in the valence rings. So as the insulator gets into the copper, it adds a little resistance. It adds a little more. It adds a little more. So typically, it would start out with good, and it would just get worse. It's almost like this is closing up. The more corrosion it gets, the more this closes up, the less amps are going to flow.
It's like those wires that crumble, basically, is like.
Yeah, exactly. If you find a bulb is dim and you look at the wires and the wires are kind of green and corroded, you already found it. That's your problem right there. Make sense? Now there's other things you could consider, like if they chew the wire and now it's bare copper, and let's just say that touches to a ground, you may make a short, which would mean this is blown wide open and there's tons of amps, but that would probably cause a blown fuse, assuming it's wired correctly. If somebody wires it with no fuse, that could cause a thermal event. You must know, right? So there is two things the mice do. One, they take away the waterproofing, and that allows for corrosion, which adds increased ohms. But two, that insulation also prevents the electrons from going to ground somewhere. If they chew two wires and the two wire copper touch, now you have two wires that are shorted. That is a short.
But is there wires that come with fuses too? I've seen stuff
Every
like that.
every factory wire in the car that should be fused is fused.
I mean, I'm sorry. Let me not in the fuse box. There's usually a fuse like connected to the wire or something like that, or is that just like stereo stuff?
You back it up from the factory, it's all fused.
Okay.
If you add something, you add an amp, you add LEDs, you add something. If it's a good kit, it should come with the fuse, and the fuse should be installed, and you should be good.
Okay.
If for some reason you don't go with a kit and there is no fuse and you don't fuse it, that's when it gets really sketchy. That's one of the main points of this class, is knowing what's safe, what's not safe. And so non-fused, if you have a big reduction in the resistance and the ohms, and you have tons of amps flow through, that makes a lot of heat. If there's no fuse, it could actually be like a short. It'll send too much amps through the wire, and that wire will get really hot and potentially catch fire. You know, so before that happens, if it's wired correctly, it blows the fuse. So the big amps and stuff, they have a big fuse right there by the battery. When you add the big 4 gauge or the 2 or 0 or whatever, they should have a big fuse right there. If you add the LED lights, they should come with a fuse somewhere in line. But as for sensors and things, those are such low amps, we don't need to fuse those. Kind of makes the ECM the fuse in a way, but usually they've got stuff in the circuitry that'll actually turn power off before it damages itself. But this is the overall. We'll talk more about the application soon. All right, so here's another visual for your Ohm's law. Like we were talking about, if we increase, let's just say the volts remain the same. Like this guy right here, he's the same guy. He's not pushing with more force here and less force here. The voltage would be the same. So that's the same amount of effort. If you add a whole lot of resistance, you're not going to get as many wheelbarrows full, right? If it's a little bit of a shorter trip, you could get more flow here. If it's got more resistance, this is going to take longer. This is going to be less flow. Makes sense? Mm-hmm. You could imagine, don't you think this top one's going to be a little faster? You're going to push up the hill, and then you're going to be like, flat, hurry up. Here you're going to be like, it's uphill, it's uphill, it's uphill. If you look, in a way, the resistance is kind of more the height, just for the record. This is going to be easier, this is going to be harder. That's another way, right? We looked at the fire hose last couple weeks ago. Now you're looking at another visual. And so if you were to look, we've got the meter set up here where you can measure the amount of voltage, and that's gonna tell you a lot about the circuit. First, you got to understand the Ohm's law. So if right here we have this meter is set up to do what's called a voltage drop test. We're seeing how many volts are dropping right here. The more resistance there is, the more volts will drop. So if this is dropping this number, right, 0.12 volts, that's actually pretty good. That's low. That means if it's leaving the battery at 12.6, by the time it gets to this light bulb, it's around like 12.49. So that's pretty good, right? This bulb's gonna be happy. This is a way that we're testing, but it's really all based on Ohm's law. Will you do the calculation on the car? No. I have never had a customer come in and say, hi, I would like you to perform Ohm's law on my electrical circuit. They just say like, hey, my bulb is dim, my light bulb is out, my starter doesn't work, right? But in your mind, you have to understand kind of the functions of electricity, how it works. If you were to be designing electrical circuits, you may have to do Ohm's law. But generally, what we do is this. We take the meter, we measure voltage drop, we measure available voltage, we can measure, we can measure a lot of things, but it's really easy to get confused. There you are measuring things, and you end up going off in the wrong diagnostic path, and you're in the weeds and you're not figuring it out, and it's kind of a nightmare. So you got to understand this to be able to do this. Really, that's what I'm saying. Cool. So, like I was saying before, in that Ohm's law, just shooting some more things out there. If the voltage is doubled, think about that, and the resistance stays the same, the amperage will double. Visualize that. In this picture, the ohms stay the same. Okay, so let's pick this one. What does doubling the voltage look like visually in this picture?
Increasing the
No, not exactly. Or let's more talk about this guy makes the pressure, this guy makes the volts, right? Yeah. Increasing the voltage by double would make this guy
go faster.
Yeah, but what would happen with him? How could he make double the force?
Get another person.
Yeah, 2 amigos, dos amigos. You have 1 amigo? No, you have dos amigos. You remember the memes? You know what a meme is. Don't you tell me it's anything other than a meme. You spell it, you still tell me it's not a meme. M-E-M-E, meme. That's how you spell it. That would be like, you seen those memes where the people are like, every job's a two-person job. There's two people doing everything. Okay, two people here. This one pushes the wheelbarrow, the other person pushes the homie. Okay, why? I don't know. I'm just saying that's visually what doubling the voltage would look like. You'd have double the pressure. Then yeah, you're gonna push that sucker right up the hill. Wouldn't you say you're gonna increase your amps? You could do, in theory, double the work because you have double the people.
So let's say this guy on top and he's pulling it with the rope.
True, there you go.
And he's
Exactly.
okay.
Yeah, so, but they'd have to be of equal strength, right? Because we doubled it. Now, if you went up by 1.5, maybe that just means you got rid of this dude and you got one that's pretty big, you know what I'm saying? But this one doubled it. You're just visually saying there's more electrical pressure. There's double the volts. You know that's gonna increase your amps. How much? Well, that's what's interesting about it. If this was 1 volt and now you made it 2 volts, but your resistance is still 1 ohm, it's going to be 2 amps. That's what I'm saying. There's a mathematical calculation that could be performed, and the electricity will follow that every time. And that's like science. That's actual science. You can test it and predict it, and it'll be observable. Cool. So understanding that, that's a really cool, that's important for you to know, but that's not normally what we deal with. What we normally deal with, usually when a circuits fail, it's because the current flow is too low or non-existent. Cool. Nobody says, oh yeah, my headlight is like twice as bright as it's supposed to be. That's just not something that, I don't even know how that would happen. How would you possibly get 24 volts going to a headlight on a system that only makes 12? It's just, I don't know how you can even do that. Maybe it got struck by lightning. It's probably not going to last very long. I've seen a couple of those. So this is a true statement, theoretically, but you're not going to experience it. This is what you're going to experience. The headlight is dim, the headlight doesn't work. The starter doesn't work, the starter cranks slow, right? These are the things we're going to actually experience. So if it's, remember what it says, the current is too low or non-existent, it may be due to the resistance being what? What happened to the resistance? The resistance went too high. So if you have too much resistance, that's when you're going to get some of these concerns, like your bulb is dim or it's non-existent. Non-existent meaning it's out. Make sense? So why do we have high resistance? Well, maybe corrosion. Maybe the wire is like, if it's way too high, the wire could be cut all the way. It could be totally broken, totally disconnected. That would add a lot of resistance. That would make it so the current flow is non-existent. Non-existent isn't open. The current flow is too low would be like a high resistance. That would be like there's some connection, there's some continuity, but not enough. Not as much as they're supposed to be. Kind of can tell the difference. Looking for something.
Loose connection made
Yeah. Yeah, like have you guys ever done something with a battery and the car won't start or something and you wiggle it and then it starts? It's probably a bad connection right there. That could add too much resistance. It's probably not a non-existent, but it's a too low. Not enough to start the car probably. Cool, so these types of things. Now, this is very practical for you. Performing a voltage drop test on both sides of the circuit will help identify any voltage drop. All right, so we're going to back up. This is a voltage drop test. I need to know, is my problem on the positive side or is it on the ground side? So if I test my positive side, and I'm telling you just because I know, you don't know yet, but this is a chicken and the egg scenario. You know that one? Which came first, the chicken or the egg? I want to teach you how to measure, and that's kind of like the egg, but I also need you to understand the theory, and that's the chicken, and I can't give you both at the same time exactly, so I'm kind of going for the chicken, and then we're going to do the egg. However, your textbook actually has laid out the egg then the chicken, so you know. A lot of times they could switch it up. So for me, I want to focus a little bit more on the theory, and then we're going to focus on the how to measure. Cool. So if you're lost on how to measure, that's normal. That's because I haven't covered that yet. and I had to pick one, so I picked the theory. Cool. The good news for you, I'm going to throw in a couple little bit of measurement things here and there. That's why this is Ohm's law and circuits, and then not necessarily DMM usage and measuring in voltage diagnosis. Make sense? So we measure right here, 0.12. That's very little drop. That means there's very little resistance right here. That means the positive side is good. If there's a problem with the bulb, we need to continue our diagnosis. If this side tests good and this side tests bad, we know the problem's over here. That way you're fixing the right side. You're not fixing the wrong parts. Like right here, you could try to fix this battery terminal, but if you're gonna fix the battery terminal, you wanna get paid for it, right, or no? If you wanna get paid for it, that's great, but you can't be wrong and billing the customer. That's not right. So rather than say like, oh yeah, you need new battery terminals, we need to clean them, we need to grease them, we need to do all this, like you better make sure that's actually what's wrong with it, rather than just fixing stuff and then go to the customer, well, I cleaned your battery terminals. Oh, great, how much? $50. Cool, so it's fixed? No. Well, why am I paying $50 if you didn't fix the car? See what I'm saying? So if we measure this, boom, and we get a good number, just trust me that it's a good number, the problem's not this battery terminal. Now, you might see some corrosion, you might see some issues, cool, but the way I'm trying to train you up is the way that I think is right, and I'm really confident that I'm right. You want to diagnose what the actual problem is, cool? So if we do this and this side measures good, and then we do this and this side measures bad, and we diagnose it as a bad ground, we go to the customer and say, hey, your ground is defective, it's going to be $50 to clean the ground, and that'll fix the car, we know because we measured it. But, you know, you should also probably do the battery terminal maintenance. They'll be like, well, why would I do that? Well, because they're corroded and this is going to cause you a future issue. And then if they say, is this my problem? No, right now, this is your problem. So if all you want to do is fix your problem, we just fix this. And they say, yeah, I'm cheap, $50, here you go. I don't want to pay the 100. We fix this, it's fixed, we're good. We're very clear conscience to take the customer's money in exchange for the services rendered, which is we fix their fine piece of equipment. Vehicle, probably really nice, especially that they didn't want to do the maintenance. So when you don't maintain something, it usually has more problems, right? So we take their money, cool, we're good. That means you knew what you were doing because you diagnosed it, then you fixed it. However, in another week, they're like, hey, the problem's back, and you say, hey, remember I told you should clean your positive terminal? Did you do that? No. Well, I'm going to charge you to diagnose it again, and this time we measure over here and we get a bad number, then we're like, yeah, you need to clean your positive battery terminal. Typically, we'd end up charging more, by the way, because we charge for our diagnosis. So they could have just done the maintenance for $50. Now we're going to charge them $50 to diagnose it. It's probably going to be more, by the way. And then we're going to charge them another $50 to actually fix it. So like they probably should have done the maintenance. Makes sense. But that's the way that I recommend you go about problems. The way that people who don't really understand this business go about it is, well, I see something wrong. I see corrosion. I won't do any diagnosis until you fix what I see. Listen, you're going to work on cars, and the more you know, the more you see. If you pull a car in, even if it's pretty new, I'll pick out 10 defects. I can't say fix all these defects before I even look into your concern. That's just not a good business plan. Make sense? We fix the customer's concern by diagnosing the actual problem, and then if you fix their concern, then I'd say you've kind of earned the right. You've earned a little bit more of a you're a little more trustworthy. You're a little more like, you fix my problem, now go for the maintenance, cool? But the other way around, you'll have lost all my respect. If you're like, let me suck off all the gravy maintenance, let me do the battery terminal clean and the wallet flush and flush the wallet out and get the gravy ladle and get the big gravy straw. We changed this fluid transmission flush and all this stuff, but you didn't fix the issue. Like, we just can't be friends. We just can't be friends like that. Make sense? Fix the issue, then you can sell the maintenance. Cool? So linking that back in, here's where we were. Remember, the voltage drop test can tell us, if we check it on both sides, it can tell us, is it on this side or is it on this side? And then we can even go a little bit further. We can test our way to the defect. And then you'll have a bad measurement, and then you'll perform a repair and you'll have a good measurement, and that's how you actually fix it. Make sense? Now, if it was plumbing, you know, with plumbing, you probably see the leak by looking at it. Makes sense? With plumbing, a lot of times, you know, it's much more visual, and that's why we're spending so much time on the theory. With electrical, you really can't see it. I look at a switch and I think the switch is good, and I test it and it's bad. I look at a wire and I think the wire is bad, and I test it and it's good. You know, so your eyes are going to deceive you on this electrical thing because you don't really see the current flow. Whereas with plumbing, you know, a lot of times you can see what's up with the water. If you thought that a pipe was blocked off, you know, you might actually do a pressure test before and after, and if the pressure was high before and it's low after, that would actually be just like a voltage measurement. It'd tell you the pipe is blocked, but before you do that, you'd probably like look inside of it and be like, oh, this pipe is got all this calcium buildup, and the passage is really tiny, you know what I'm saying? So in electrical, it's a lot of measurement and understanding and not being able to visually see it, unfortunately. Cool. The good news is, though, this type of work tends to pay well because the common person can't do it themselves. So that's a good thing for you. All right, and then a resistance check of the electrical device will indicate high resistance. So what this is kind of saying is like, if you can measure the voltage loss, that tells you about the resistance. Because Ohm's law, they're locked in. It's a predictable, there's a calculation, cool? So your resistance loss will tell you that your voltage loss will tell you the resistance level. Or if you measure the resistance, that'll tell you how much voltage will be lost. Make sense? So because they're directly correlated, and you'll see when we do this formula. So if you understand these two things, it's important. Now there's one thing I'll help you to understand just a little bit here. Right here, we measured a voltage loss called the voltage drop, and 0.12 is really good. That 0.12 voltage pressure being lost tells me this circuit's open. If you'd say it's like clear, it's clean, it's a pipe, that's got a good flow through it. It's a nice, not restricted system. Because we've only lost 0.12, 0.12. That's great. That tells me my resistance is good. But the other way I could do this, I could disconnect this system and I could put my meter like this and I could change this to ohms, click, click, and then I could get the ohms and it's going to say 0.2. You just tested it in two different ways. You agree? You can visualize that, right? The meter can test the resistance or the meter can test the voltage at different points. Both will indicate the same thing. However, one of those tests is superior to the other. And I'll tell you why. When you measure resistance, this uses its own little 9-volt battery, and it just sends a tiny amount of electrons. So visualize that pipe. If that pipe's got a bunch of calcium buildup in it, and it's down to like a tiny little pinhole passage, if you use the 9-volt battery, those electrons will slip right on through. It's very low amps on the 9-volt battery in this meter, and it'll be like, oh yeah, it was easy. I went right through the little pinhole and it was easy, right? So you'll think the pipe is good. But if you actually measure the system with the full current flow through it, measure the system active, you'll be like, hey, wait a minute, I'm losing a lot of volts. This pipe is clogged after all. You want this explained in medical terms? Anybody ever had any heart testing done? You know, like blood pressure stuff. They'll do a thing called a stress test. They'll roll you in and they'll check your blood pressure and will be like, oh yeah, I think everything's cool. But if they really want to test you out, you know what they'll do? Put your butt on that treadmill and be like, just go for it. Just go full speed. And then they'll be like, uh-oh, we think you got some plaquing in your arteries. Plaquing in your arteries is like the same thing as resistance in your circuits. So if you want to have a really good test it on the treadmill. What I'm saying is like, resistance is kind of like just doing the basic test. The more detailed test is actually measuring the voltage drop. Measuring the voltage drop is testing it while the circuit's trying to work at full capacity, and you may detect more defects than if you were just do resistance. Kind of translate? Not to worry. Next week we do more on the meter, but just for your reference. Remember the chicken and the egg? All right, so like I was saying, this is the battery, that's the source. This is the switch that controls it. This is the load. The load does the work. In this case, what is the load?
Light.
Light bulb.
A light bulb. And what work are we getting from this light bulb?
Light.
Yeah, light. That's going to be light. Boom, and there it is. Poof, just like that. So how we're really getting at is 12 volts coming out. It's going through the switch because the switch is closed, so that gives it a pathway, right? It goes to the light, and then the electrons are going to go through this tiny little filament right there, and to ground. So if we were to look at this, and by the way, we're going to do a little bit of voltage prediction, but that's going to be more in detail. Actually towards the end, but a lot next week, okay? If we were to look at this, what I could tell you is we should have about 12 volts right here, about source voltage right here, and we should have about 0 right there. And the way that I know that is because I understand Ohm's law, but the way you're gonna know that is, remember that story about the parents giving the allowance? The parents are handing out, don't spend it all in one place now, $12.48. Who gets the $12.48 in this case?
The light bulb.
The light bulb is the only child. So the light bulb's like, oh, thank you very much. Okay, that's how it's supposed to work. The allowance is supposed to be passed down through the wires and all go to the load. That way the load is able to do the most work. Make sense? However, if we were to look at this system has a defect. This bulb is really bright. This bulb is slightly dim. Not super dim, but a little dim. It's almost like the bulb is only getting like maybe 11.3 volts, not a full 12.48. Now, how did that happen? Well, if you look at the circuit, you don't know. And that's kind of the point. You look at these wires, they look good. You look at the switch, it looks good. Everything seems fine. But when you measure it, we go ahead and we measure the bulb. Hey, bulb, how much voltage are you consuming? And the bulb's like 11.3. I'm like, wait a minute. But I checked the battery voltage, and the battery voltage was 12.5. So you do another measurement. You measure from the positive battery to the end of the switch, and you notice it's dropping a 1.2 volts. So in the lesson of the allowance, the parents handed down 12.5. The only child only got $11.30. There's an issue there. Where is the issue? That's the question. Make sense? And you can measure. So we measure from here to here. 1.2 volts is what's called excessive voltage drop. Why are we spending 1.2 volts? You want to make it money? Money makes sense to you? Parents passed out $12.50. Why is it costing me $1.20 just to get on these nice, clean, clear wires? It shouldn't cost that type of money. I don't want to pay that type of money. Basically, these roads should cost you about like 0.1 volts, maybe 0.2 volts. That's like 10 to 20 cents. If you use a road right here and you got to spend $1.20 just to use this road with a little tiny bridge, someone's overcharging. Who is it?
The bridge.
It's probably it's the express lanes. In this case, it may very well be the bridge, right? I mean, you're kind of being scammed. You're paying taxes on the roads, and then you're paying tolls on the roads. What a scam!
What's that one again? That little one right in front of the battery?
Here?
No, the pathway.
Okay, this is a fuse.
So it's a
All right,
okay.
so, and that's kind of the thing. I agree it could be the bridge, but I'm going to break it down for you. With this measurement, all you know is that it's charging you $1.20 between these 2 points, and that's too much. Is it the bridge? Maybe. That's a switch. Is it the wire? Maybe. That's like a road. Is it the fuse? It could be. I don't know. But that's kind of the point is, in one measurement, we know that we're losing $1.20 right here. The problem is we don't know which one. So you know what we could do real easily if you're the technician? Move this lead right here and test only the switch. Whichever is between these two leads is what you're testing. Cool? So we could move it here and be like, oh yeah, the switch is costing us $1.19. I'm like, freaking rip off. Take that switch out of there. Put a new switch in there. New switch only costs you 10 cents. Like that. Make sense? Then that would repair the circuit, and then all the voltage, all the money would be spent back on the only child, the bulb. In every circuit, there's a load. Typically, there's one. Sometimes there's multiple, but typically there's supposed to be one. As the circuit's designed, there should be one load in this one. But unfortunately, we're losing some voltage drop here. Kind of makes sense a little bit. So the more, remember in Ohm's law, the more resistance we add, the lower the amperage, right? I'll prove it to you with a very complex calculation. This guy pulled up more. This one didn't flow as much. Do you agree with the visual? So if that's the case, we've added resistance on this part of the circuit, which means less amps are going to flow, which means this bulb's going to be a little dim. The amperage being less will make the bulb dim. Cool? Kind of crazy, huh? All right, so we'll continue. All right, so when we talk about circuits, that's the next thing we're on. Made up of components and interconnecting conductors. Generally, that's wires. Technically, it doesn't have to be wires. It could actually be a printed circuit board, right? So in your computer, there are some wires, but mostly there's all these little circuits that are printed on that green semiconductor chip. Yeah, on the different various boards and types, right? So generally it's wires, but they're arranged to manage and control the flow of electrons to what? Perform specific electrical tasks. Pause. This switch was made for one reason. What do you think this reason is? Well, to connect what? Yeah, because we want light. That's it. So if an engineer sits down and they're like, all right, what do we need in this car? And they're like, oh, we need a dome light so that way you can see what you're doing in the dark when you get in or when you open the door or whatever. They'll design a circuit and they'll be like, okay, I know what we'll do. We'll connect it to the battery. That's pretty much where stuff gets connected, at least eventually. We'll send it through a fuse so that way everything's protected. Cool. Then we're going to go to the switch. Now, if you open your door, you want your dome light to come on, right? So let's make the switch in the door jamb. You open the door, switch closes. When you close the door, what do you want to happen to that dome light? You want to drive with that thing on? No, me neither. So when you close the door, it opens the switch. See, it's a little backwards than you think. So right here, the door is open. When you close the door, this switch opens. So if you open the door, the switch closes, electrons should make it to the light, and what should happen? See, I can't make light, but I can make sound. That's how you know it's on. Cool? That's how this circuit was designed. It was designed for one purpose, and that is when the customer opens the door, we want the dome light to come on. Fair enough? Now, if the customer opens the door and the dome light doesn't come on, that's when you get the car. So I like cars, but not like I did when I was young. The only time that people bring their cars to me is when. So they're not like, hey, check out my car. We'll sit and we'll talk about how cool it is. And, you know, it's more like, hi, my dome light doesn't work. Can you fix it? And I'm like, all the cars are junk to me. I only see them in their worst place. I only see them when they're broken. Every car I really am honestly involved in has a problem. It's got the dome light is out, the headlight is out, the check engine light is on, the transmission slips, the engine's knocking, right? So they're all, that's why I lost my hair. All these problems be coming at me, and every problem car takes one hair, and that follicle closes up. It's like, I'll never produce again. You know, this is what's happening, I'm telling you. So now you understand the purpose of the circuit, kind of, right? And so this is what it's saying. We manage and control flow of electrons to perform specific electrical tasks. We just did the dome light. Whatever electrical thing that you know about, it's going to be the same story. Name it. What's your favorite electrical component in your vehicle? Pick something. There you go. We send electrons to that radio in several different ways so that it can perform a task. And what's interesting, the radio is a fun one because we send 12 volts to it and the radio is going to do something else with it, and the radio is going to send its own amount of power out to the speakers to magnetize them, to move a cone so it can basically magnetize, and the cone is going to push air, and that air is going to be very satisfying to your eardrums, I believe. That's the task of your radio. Makes sense? That's literally its job. To manipulate electrical signals and send them to a magnet that pulses the air, and that air pulses the air to your eardrum, and you go like this. Huh? I like this. It's my favorite song. I don't know what it is, but you do. That circuit was made for that. Now there's different configurations. There's something called a series circuit and a parallel circuit. And then there's one that's in between, but let's first just briefly discuss a series circuit. A series circuit means there's only one path. So luckily we don't have a whole lot of that when it comes to roads, but just imagine there's only one way to get home, and that's the only way, period. What happens if that road is damaged?
You can't get out.
Period. Exactly.
Like a
So
tree.
in a series circuit, all the electrons have to go through the same path. Cool? In a parallel circuit, there's multiple different paths. The Ohm's law still applies, but the way we calculate, some of the measurements we do are a bit different. You know, we do them slightly different. Cool? That's the way it's going to be. And then there's in between, which is kind of accurate with our roads. There's series parallel. So there's some part that's series and there's some that's parallel. So you have to use this freeway, but then after that you could use any one of these 5 different roads. Make sense? Starts out series and then it goes to parallel. Pretty neat. And then don't worry, we're going to do a whole lot more on circuits next week. A bunch more. We're still going to do some more right now. Cool. Alright, now when we talk about Ohm's law, again, it's the relationship between volts, amps, and ohms. And it always balances. So it always, mathematically, it always works. Cool, so when we talk about these, you got to consider that. Now, if the resistance stays the same but the voltage rises, remember, it pushes more current. If the resistance stays the same but the voltage decreases, it pushes less current. Interesting. Remember? And then the total current flow of a circuit in amps always equals the voltage divided by the resistance? Ah, so that's your first experience of this formula. If you were to do volts divided by ohms, you will get amps. What? Yes, you can do this. You can do this math. We're going to do this math. There is your formula. Volts equals amps times R, R being resistance, exactly. V for voltage, A for amps. And then the voltage can vary across different points in a circuit, but the current at any point can be found without an ammeter by using Ohm's law. So this part gets a little tricky because when we look at the total circuit, we look at the actual source voltage, okay? Then within the circuit, that electrical pressure gets used up in a way, right? It's like the allowance money. So when we're trying to do this calculation, we're generally really doing the whole circuit. So the whole circuit is powered by the battery. So if we were to measure the source voltage at 12.6, that's the number we'd use. And that'll tell us, well, it'll tell us whatever we need to know. If you know any two, you can determine the third. If you know volts and amps, you can determine the resistance. If you know volts and resistance, you can determine the amps. If you know amps and resistance, you can determine the volts. See, I'm saying it's algebra. That's why there's only 3. V equals A times R, and you can switch that around to determine the others. All right, so here we go. Let's do this. This is really fun. Okay, this is so fun. What do we know about our circuit? Let's say we know the volts. Let's say we know the resistance, but you don't know the current. Do you know what you do with this circle? Cover this one. See, if I covered this, what do I have left? V and R, right?
Yeah.
So do volts over R. You know what that means? Volts divided by resistance. Yeah, volts divided by ohms. If it was 12 and 1, 12 divided by 1 is what? 12, then you have 12 amps. Cool? So you take this, whichever one you don't know, just cover it up. You don't know volts? Cover it up. You want to know volts? Do resistance times amps. If the resistance was, what did we say? It was 1, and the
12.
amps was 12. What's 12 times 1?
12.
It's 12. There you go. Every time. It works. All right, so here's the example given. In this case, here's your battery. We simplify it at 12 volts. You could do 12.6, or you're just making it more difficult on yourself. 12 volt battery, that's the voltage. How much is the resistance of this load that you don't know what it is? Maybe it's a bulb, maybe it's something else.
4.
Okay, but what's the amps? You don't know, okay, for now. So if we have 12 volts and we have 4 ohms, we know the voltage, we know the ohms, we don't know the amps. Cover this up. 12 over is divided, right? 12 divided by 4. Do you know the number? 3 amps. Every time. Every time. Cool. Now you can do it. I'm gonna, you guys follow this, right? Because I'm about to ask you some questions. You want to do it one more time? All right. We're going to do it several times. Mostly you're going to do it. So this is again what it's talking about. Using the rules of Ohm's law, give us accurate method of determining values in an electrical circuit. The value of V and R are known. You can find A, V divided by R. Okay. If this makes sense to you, cool. If this doesn't, let me demonstrate it for you. If the value of V and R are known, to find A, V divided by R. So V and R are known, you want to find A. Ready? Here's another way to do this. Oh, and by the way, this is EIR. So depending on who you listen to, it's VAR or EIR. So we knew, what did we know? We knew V and R, right? But we don't know A. Honestly, I don't remember those formulas that well. I do this. Cover it up. Now I got volts divided by resistance. That's what I do. So this picture, if you want to get good at this, you need to get a tattoo. Don't put this one on your lower back. You won't be able to use it. You need to get this on somewhere where you can see it and be like, oh, I could do Ohm's law.
Right there.
Oh, yeah. Makes sense? You can do that. If you got it and somebody saw you, they totally know, like, you're in. You're part of the club. If you want to join the IBEW, you know what that is? International Brotherhood of Electrical Workers, you could get the Ohm's Law tattoo. But that's really for electricians. This is what's cool. Electricians and us, we still use Ohm's Law. They know Ohm's Law, we know Ohm's Law. The electricians tend to look at more like Kirchhoff's Law because they're worried about how much power things draw, but Ohm's Law is Ohm's Law, whether on a car or a house or a solar PV plant or whatever, you name it, generator, it's the same stuff. Cool? So that's what these circuits are saying. That's what all these words are. Similarly, V and A are known, and R can be calculated, right? So if you want to calculate R, cover it up. V divided by A. Yes? You like it? And then the last one is if R and A are known and V isn't, cover it up. R times A will give you V. Yes?
Yes.
Yes. Now, in other words, though, you may see VA. I like VAR, volts, amps, resistance. It just comes to me more naturally. But sometimes you'll see this formula EIR. E is electromotive force. That's volts. I would just rather make it a V myself. But you may see this and you might be like, what the heck is this? This is still Ohm's law right here. It's just using electromotive force. I is current flow, is amperes. R at least is still the same. So V becomes E, A becomes I. It's still the same formula. I did like this picture because you can see someone is covering these different points.
So you can just get a tattoo of the colors and just write them in when you're working on the car.
Here you go. All right, now in full transparency, I'm going to tell you the truth now. You will probably, more than likely, never actually do the calculation when you're working on a car. Yes. However, I learned this pretty extensively, just like you did, and the whole time I'm like, why do I really need to know this? But my instructor at the time, long time ago, Hudson Valley Community College, we call Harvard on the Hudson. It's definitely not Harvard. The Hudson is like, sounds cool, right? But if you live in the area, the Hudson River is like, ooh, that's nasty. With that being said, I learned all this type of stuff, and the instructor was absolutely right. You need to know this from a theoretical standpoint because you have to comprehend the information on the car correctly. But we don't really do this calculation. You know, just being real with you. You're not gonna do the calculation. Cool. We're just, you know, this is for understanding, for science and things. Cool? Okay, here's some other numbers. Here you go. We're gonna do this together. Put this up, and hopefully it's not gonna totally ruin the quality, because I'm allowed to write.
Just not on the screen.
Exactly, and I'm being pretty good today. I think this one's good. All right. We don't know. Do you guys remember what this one is?
Or volts.
We could say V, right? So we do 4 ohms times 6 amps. I'm gonna make this really simple. 4 times 6 equals, cool, 24. So what system do we have? It's a 24 volt system. Cool. Let's do this one. You have 12 volts, you have 3 ohms. So what's missing over here? All right, so now we do 12 divided by 3. So we're gonna do it like this. 12 divided by 3. 3, 6, 9, 12. 4. Cool? And that's literally just how you do it. If you really wanted to, you could probably go online and get an Ohm's law calculator. And you could just punch the numbers in, but you really should be able to do this too.
Pretty simple.
It's not that hard. Definitely not. Okay, so we're gonna do a little bit more practice mathematics. Go ahead, shoot it.
Are you able to do one where it's just volts and amps and no ohms?
Sure. And that's what we're gonna do on, I think, one more slide. We could do if you know 2, you can determine the third. As long as you know 2, that's all you need to know. Okay, let's make some numbers up here. All right. Give me the numbers you want. You asked. What did we know? We knew what? We knew volts and amps, right?
Mm-hmm.
So let's go with 12. Let's go with, I'll make this one super easy math. 1. Don't shout this out, people. This is practice. 12 volts, 1 amp. Okay. I'm going to give you a little time. I'm also going to build this into a question on that video, just so you know. Okay. Let's think about the formula. Let me walk you through bit by bit. We don't know this one, so cover it up. We do know this one. We do know this one. This one's kind of over top of this one, right? That's why the circle's nice. 12 divided by 1. Who can help me out? There we go. 12, but it's 12 what? 12 ohms, right? Because we didn't know the resistance, so that's 12 ohms. If you have 12 volts and you have 1 amp, I promise you the circuit is going to be 12 ohms. It's just science.
Is there something in the car that is 12 ohms?
There would have to be in the circuit a load that's 12 ohms. Maybe you have a 12 ohm bulb.
Okay.
Exactly. So let's say you're an electrical engineer. You're engineering, you're doing things that engineers do that I don't do. I'm not gonna lie to you. If you do that, you'll be like, okay, I have a 12 volt system. I'm putting 1 light bulb in that equals 12 ohms. How many amps is that going to be, right? We look at that slightly different. So I gave it to you as the electricians have it. They have a 12 volt system. They have a resistance of 12 ohms. If you look at this is your calculation, right?
Yeah.
12 divided by 12 equals 1. 1 what? Amp, exactly. So now, if we're the electrical engineer, we're gonna be like, oh, okay, this system, do the calculation. Okay, 1 amp. What that tells me is what size wire I need to run, what size fuse I need.
Is 1 amp a lot for a light bulb?
1 amp's very low. That would be great. That'd be like maybe one of those little peanut light bulbs, a 194 bulb for a license plate light or something. Something like that. So now if we do this, right, we know we're gonna have 1 amp of flow. Not speaking as an expert here. The electricians, as I understand, are gonna round this up to probably like the next real available size. And fuses in automotive, typically the lowest I see is a 5 amp. So if we have a 5 amp fuse, in fact, I could do a quick calculation. Let me jump out of this for one quick second, make this super practical for you. Wire ampacity chart, you must know. Let's look at images. Let's go with copper since that's more typical. Open a new tab. Actually, should have been open image a new tab, but I think this will work. Alright, this is going to be like way too oversized, but I'll give you the lesson first. Alright, if you are going to flow, let me look, I believe that's amps. I really want to find one that'll do us a little better. Conductor size, 20 amps. Okay. So if we're going to build an electrical circuit and we needed 20 amps, it depends on the temperature first off. If it's going to be 140 Fahrenheit, we would use these. But if it has the potential to get to 167, we'll work off this chart mostly because I'm closer to it. If we're going to build a circuit that's 20 amps, this is going to show us we need a 14 gauge wire. If you want a circuit that's going to do 25 amps, you can do a 12 gauge wire. Or if it was going to be at this temperature, because it's a little bit cooler, if you want a 15 amp circuit, you can do a 14 gauge wire. This is the size wire you need to buy. Okay, this one is really more for like high current. To do something for 1 amp, that one actually might be a little tough to find. 1 amp AWG is American wire gauge. Let's see if we can find one. I mean, the thing is, we're working, it's so small. That's kind of the thing. It's just so tiny.
So the 1
I
amps
don't
are
know
like
about
the ones are like tiny little wires, tinier than the ones that go to the headlight, basically.
Okay. A 15 amp wire is 14 gauge. That's actually small for like house stuff, but for a car, that'd be pretty big. We see a lot of stuff in a car, 22 gauge. The bigger the number, the smaller the wire. And the way I understood it, don't 100% quote me on this, but the way I understood it was, it's how many wires, it's how many of those you can fit through. I think it was like a 1/2 inch hole, or maybe a 1 inch hole. So you can fit 14 of them through that size hole. That's why it's a 14 gauge. But if it's a big wire, let's say you could only fit 12 of them, that's a 12 gauge wire. Let's say it was really big and you could only fit 3 of them, that's a 3 gauge wire, right? So the bigger the gauge, the smaller the number, the bigger the gauge. Cool? The bigger the gauge, the more amps it can flow. So if you're an electrical engineer and you just did this calculation and you're like, oh, I only need 1 amp, you're seeing I'm struggling. I don't even know if you can really buy actual wire that's 1 amp. 1 amp is so low, you could run it probably on like a Cat 5, like some little Ethernet wire, you know, which they do, by the way. They do power over Ethernet. You can plug in Ethernet and also run power, and they'll actually run the power through the Ethernet wire. Those wires are ridiculous tiny. You know that. So more what, you know, like an electrician would do is be like, okay, somebody wants to do an EV charger, right? You know, EVs, it's a thing. You want to charge your EV charger. Typical EV charger would pull at about 32 amps. You could probably go to a 40. If you go to a 30, you're not safe, right?
Because you're at 2.
Right, because you're 2 amps over, and this wire is only rated for 30. So you really can't run a 10. You really need to run an 8.
So it's not closest to the numbers that what
Exactly. You got to round up. You got to be above and beyond. And this is what I want you to understand. If we're set up to run a 30 amp EV charger, a 32 amp EV charger, 30 is not enough. You actually have to go to a 40. But you could put a 40 wire in, which is an 8 gauge, and you could put like a 35 amp breaker. But the truth be told, I mean, if this wire can handle 40, you just put in a 40 amp breaker, which is the fuse, okay? The fuse is always based off of the wire, and the wire is always based off the Ohm's law, you know, the actual calculation. How many amps is this system gonna draw? If it's gonna draw, let's say you have like eventually maybe I'll get the Hummer EV, but maybe when the price is lower, and plus, you know, I got a Hummer now and I kind of like the way it sounds and stuff, so anyway, someday, if I get that, I may want like a big charger, because that thing's a little, you know, gas guzzler? I can't call it a gas guzzler because it doesn't use gas, but those use a lot of electricity. I may want a 100 amp charger. That'd be really cool, but you want to know the problem? Look at the wire size I need. 3 gauge wire? No, I'd have to run all new wire for that. Like, houses don't normally come with 3 gauge wire going to random places. Nobody does that. Entire houses used to be run off 3 gauge wire. So if I want to put that type of charger in, I got to pull new wire. I can't just shove a 100 amp breaker in some wire and try to charge it, because it's going to overload the circuit. It's going to pull too many amps. It's going to get too hot. It's going to burn stuff up. Cool. So, and then if you look at like a more like, if you make a house right now, they're going to probably put a 200 amp service in. This is what's called 3/0. So that means not even one of these would fit through the hole. You need like 3 of those holes to fit one. 3-0 is huge. You guys have done big audio systems. You know, you got the 0 gauge wire. That was like in between these two. 0's like bigger than 3, but smaller than 1/0. It'd be right there. Cool. So that's like kind of the way we figure it. Now jump back to the calculation. Mason, you speaking up? I heard a noise. Go ahead.
What would happen if, say, like, you only needed like 5 amp wire or something, and you put in like a 20 amp wire?
No problem. Love it. It's just a waste. So let's say on this one we only needed the 1 amp because we did the calculation, but we couldn't find 1 amp wire. So we go ahead and we want to run a wire that's good for 5 amps, which I didn't catch the size. So let me fib it. Okay, I'm gonna fib. Don't quote me. Let's say that's a 24 AWG, right? That's a small wire. Do you think about cost? Do you think the small wire is cheap, or you think the big wire is cheap?
Big wire.
Do you think the big more copper is cheaper? You see what I'm saying now? If you go and you're like, give me 100 feet of that 3/0 wire, and they're like, yeah, buddy, you better have a forklift because we can't even pick that up. That's gonna be expensive. Whereas if you have 100 feet of the little 24 gauge, you're gonna be like, oh yeah, I'll put that in my pocket. That's gonna be cheap. Make sense? So with engineer and plus space is valuable. So if you only need 24 gauge, they're not gonna be running a 14. They're not gonna be like, oh, let's just make the wire larger and more expensive for the heck of it. So it's an engineer's job to figure out how many amps is the circuit gonna pull, and then they're probably gonna round it up. How much? I don't know. But in this case, we couldn't put a 1 amp fuse in. They do make 5 amp fuses, so we bumped it up to 24 gauge wire. If the 24 gauge wire is good for 7 amps, I'm good to put a 5 amp fuse, because before that wire is ever in danger, the 5 amp fuse goes poof. And then the wire's like, that was kind of scary. For a second, I thought I was going to exceed 7 amps, and then right at 5, boom, the fuse died. Remember, it's like a sacrifice. The sacrificial lamb, that's the fuse. The fuse saved the wire. And the wire, you know, if that were to catch on fire, that could catch the whole car on fire, right? So that's why we really do it. Cool? So they're going to round it up. How much? I don't exactly know. Let's come up with another number, and then we'll come up with new wire. Let's say we got a 12 volt system, and let's just say we have a resistance of 1 ohm. How do we do this math? Cover it, right? Okay, so do the formula. 12 volts divided by 1 ohm equals 12 amps. Okay, now This requires a drastically different wire size, doesn't it?
Sir.
So 12 amps might be more like a 14 gauge wire, right? Because in fact, if we're at 12 amps, we're gonna round it up some. What I can tell you is a 14 AWG, American wire gauge, is good for 15 amps. Okay, so do you think that wire would be good for this application? I would say so. It's bigger. Now let me give you a bad one on purpose. I'm going to go with an 18 AWG, which is good for 10 amps. Is that good for this application?
No.
You're going to have too many amps flowing on too small of a wire, and the wire is going to get hot, and you're going to burn alive in the car, banging on it. You have to, which is why I think that you should get this car glass breakout tool and blah, blah, blah. I could totally do a sponsor thing like that. But it's not going to happen. You know why? Because the engineers did the math, and they're like, 12 amps? No. We need a 14. 18? That's a no. That's a no. Because this is what would happen, really. You'd get the 18 AWG. You put that in. You'd be like, okay, 18 AWG is good for 10 amps. Let's put in a 10 amp fuse. What's going to happen when the circuit pulls 12?
It's gonna blow the
Fuse is gonna blow, and then the customer's gonna be like, "Hey, my whatever doesn't work." And you'd be like, "Oh, let me test it." Well, I found it. I don't know anything about Ohm's law or measuring, but I found you have a blown fuse. Let me take your money and put the 10 amp fuse in there. What happens to the 10 amp fuse?
Blows.
Well, I found it again. Let me take your money again. Here at Billy Bob's Bait, Tackle, and Auto Repair, we strive to fix your car right the 4th time. Make sense? So you put in another fuse. And then you know what's going to happen? Billy Bob out there, Billy Bob's going to say, I know, it's blowing the 10 amp fuse. So you know what we should do? I'll put in a 15 amp fuse in there. Yee-hoo! Mm-hmm. If it was an old style one, they used to have these round fuses. They just put like a 22 caliber, you know, a little bullet, little shell in there. You know, and that wouldn't blow unless it did. I don't think it actually will, I don't think it'll actually make it shoot. But that's an old school, there's stories about it, the rumors. Right, so this would be a no. If they put a 15 amp fuse with an 18 amp wire, by the time it pulls 12 amps, what's the fuse do? Fuse is like, I'm chilling. I could do this all day. And the wire's like, I can't do this. It gets hot, catches on fire. Make sense? So if you didn't take this class, hopefully you weren't stupid enough, to put in a fuse that's too big for the circuit and risk burning the car to the ground. Now you understand how Ohm's law is applicable? If the circuit is a 14 gauge, sure, run a 15 amp circuit. If it's only an 18, that's a 10 amp fuse. You could put a lower amp fuse in there and it'll just blow the fuse a little bit sooner if it does go wrong, right? But you can never put a fuse that's bigger than the wire can handle, because now the wire is the weakest point in the system and wires catch on fire. Make sense? That's Ohm's law in a practical application for you. So your question was, can they put a bigger wire? Sure. If you only need 12 amps and you want to run a 12 AWG, good for 20 amps, you can do that if you want, but you know why the engineers won't? It costs more money, it takes up more space, so it's a waste. It's like, if you don't want to know this, you could also just say, well, I'll put in a huge wire every time and I'll never have a problem. That's true, but now you're just wasting money. You don't need a wire that's bigger than it needs to be. We know, because this Ohm's law is like, it's a science, it's a law, it's a formula. You don't have to be like, well, I'm not really good at math. I can't figure out 12 divided by 1, so I'm just going to say it might be like potentially up to 100, and we'll run like a big Briot. And next thing you know, there's not enough room in the car for all the wires you want to run, because you'd be a failure of electrical engineering, which I'd probably be. I don't think I could do the job very well. Mostly because I don't want to. Okay, but it's pretty scientific. Is this difficult? All right, good. Let's do another one. I think I'll leave that right there, just for memory's sake. Okay, let's just say once again, we're on a 12 volt system. And let's just say we know the amperage is a 6. We got 6 amps. How do we do this math? 12 divided by 6 equals 2. So we have 2 ohms in that circuit. Love it? Like it? Okay? All right, let's switch it up a bit in a non-automotive way. And let's just say we keep the 6 amps. Remember, we used to have 2, so I want to put a little 2 so we can remember it. And let's just say we didn't know what system it was on, and our 6 amps. Okay, let me pause on that. You already know this answer, but I just realized this is a good lesson here. If you know, this is the exact same circuit as the last one. If you have 2 ohms and 6 amps, what's that tell us about the volts? How do you do this formula? Cover this.
Multiply.
So it's 2 times 6 equals
12.
Whoa, those are the same numbers they were. Does that make sense? Now you understand Ohm's law, huh? 12. So we'd be like, oh yeah, this is a 12 volt system. Cool. All right, now we'll make it a little more interesting too. Let's say we've got, let's keep our 2 ohms, but let's just say now we have 12 amps. What's that tell us about our volts? Do you know how to do it? 2 times 12. 24. Oh, so you're saying we're no longer on the 12 volt system. So, whoops, I accidentally started writing the wrong thing. I'm so used to writing 12. Cool. Let me tell you why that's interesting. Remember I told you if you could increase your voltage, you could get more power. So they've been talking about this in automotive like for years, forever. Saying, well, we might go away from the 12 volt battery because if we did 24 volts, rather than having 6 amps, you could actually do 12. So you could get more power through things by increasing your voltage. Makes sense? You get more amps by increasing your voltage. There's a bit of a negative though. If you have increased amps, you got to have bigger wire too. And then if you really wanted to get technical, if you increase the voltage, that voltage tries to push out with more force. That means you might have to change it. 12 to 24, no big deal, but if you wanted to run like 120 volts or like 240 volts or 256 or 400, you know, some hybrid EVs are coming with an 800 volt architecture. That has a ton of electrical pressure. They got the big orange wires, and the orange wires have like a whole bunch of insulation on them because that high voltage tries to push out more. Cool. But on those hybrid EV stuff, you know, they can make a lot of power. And power is actually one of the next formulas we're going to do, FYI. So this is kind of summary of Ohm's law. If you increase the volts, you can get more amps, even though your resistance is the same. We can do it. You can prove it over and over. So let's say I give you a practical application of, it's a 12 volt system. We were supposed to have 6 amps right here, but instead we only have 3 amps. Not even doing the math, thinking about it, if we're supposed to have 6 amps, why would we only have 3?
Because there's resistance.
Exactly. You know it because you visualized it, but now you know it because of the math. So if we had, correct was 12 divided by 6, that should equal 2 ohms, but instead you only had 3, so we're doing this is the problem one. 12 divided by 3 is, you have 4 ohms, you have double the resistance because of that mouse, because of that corrosion, because of a terminal fitment, or you know what I'm saying? This is maybe what the Jeep was supposed to do, and this is what the Jeep is doing in that one. And it probably actually be a lot more. Okay, I'll prove one more thing to you, mathematically.
I have a lot more corrosion than that.
I bet you do.
But it's all by.
Well, this is going to be it. If your system's 12 volts and your amps is a 0.001, how would we do that? 0.001, by the way, what's that look like? almost no flow. Almost no, there's basically like essentially no flow going through that pipe if it's plumbing.
I think my battery's dead.
Very, 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 very low amps. So what's a 12? We might need a calculator on this one, divided by 0.001. Alright, I could agree with that, and I'll show that to you. 12 divided by 0.001 equals, you now, winner, have 12, how much? 1,000 ohms. You got a lot of corrosion in there.
What's the Jeep from the East Coast?
Yeah, it's an East Coast Jeep.
Oh, no.
Straight out of Ohio or something. Alright, so
Straight out of New York City.
New York City. Okay, this make sense to you? Let's make it even worse. Let's say you have 12 volts and your amperage is flat out 0. What the heck is that number going to be? 0. Is it though? That's an interesting one, isn't it? So we have, it's 12 divided by 0, right? What? 12 divided by 0, you can't divide by 0. That's what this, I realized you couldn't quite see it. I got ahead of myself a little bit. I broke the calculator. Okay, this is, you know what this measurement would be? We'd consider this something. Open
Circuit.
Exactly, or sometimes we'll call it OL, out of limits, right? And that's why Ohm's law and the meter will kind of align with each other. If you put your meter on there and it measures OL, that's measuring open. If it's an OL, I already tell you what the amps are going to be.
0.
Zipperoonie. And the calculators will be like, error, whatever. Windows just crashed because of that question. Cool? Alright. Good with Ohm's law. You guys feel like you understand the math? You feel like you also understand the concept?
Yes.
How you can apply it to an actual problem? Okay, but we're not done. But wait, there's more. Like a late night infomercial. Okay, energy is the potential to do work. Okay, now we're getting into power. So remember, I've given you a hard time about electrical circuits. If you're like, oh, there's power there, there's power there. It's voltage, really. Power is when it actually does work. Power is potential to do work. Work is done only when the energy is released. So that means there has to be current flow. Voltage alone isn't power. Cool? The difference in electron supply at the battery terminals creates electrical force and is called the potential difference. All right, a lot of terms here. When we measure voltage, I'm going to call it voltage. Some people will call it potential. You, on the other hand, have so much potential. That means you have the ability to do a lot. Will you actually do it? I don't know. All right, so that might be a bit of a lesson on work. Right? If there's a lot of potential voltage, but there's no actual action, amperage, you've done nothing. You've been pretty much just bumming, slumming and bumming. Cool? So that's what work is. Potential difference, and then tapping potential means converting from one form of energy to another. Okay, so like this battery has a quantity of potential energy. If we were to actually tap into that, we would take this potential energy and have it do work. What type of work do you want to do with this battery? Want to light some lights? Want to turn a starter motor to crank the engine over to build compression to fire a spark plug to eventually, hopefully, start the combustion process and where it starts taking your gasoline and turning it back into motion, right? That's how the car works. Let's just say we want to light a light bulb. We're taking the potential and we're making it do actual work. Cool. That's more like power. And then when we do converting one form of energy into another form is called the transformation. So we'd be transforming the chemical potential in here, which is the voltage, to action, which is like amps. So that would be the power. That'd be the work. That'd be the light bulb glowing. And the light bulb's work can actually be measured as well. We can measure that in lumens. So how much light energy is coming off of that would be in lumens. Cool. So we're making it do some work. All right. Now, power is the rate at which work is performed, or the rate of transforming the energy. All right. So if, let's say, I want you to, I would never hire you for this, but let's say pull weeds. There's some people who are kind of fast, and some people who are kind of slow, right? One is a high rate of work. How many weeds per hour? Boom, 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 boom. Another one is slow. Let's say it's stacking boxes. Some people are slow. Maybe in an hour they stack 60 boxes. That's 1 box per minute. What if somebody's working a lot faster?
Twice the number of boxes.
Maybe twice the amount of boxes, but what would we call that? They did double the work, twice the work. Yeah, exactly. So work isn't just the potential, work is the actual perform. Make sense? Both people, if they're able-bodied, they had the same breakfast, they might both have the same potential, but one of them actually did more work. By the way, if you were to watch them, one of them's moving twice as fast as the other one, and that makes sense. So when you look at work, you're talking about like the potential times the amps. It's the rate of speed, right? So if somebody's working really slow, they only stack 60 boxes. Somebody's working really fast, they stacked 120 boxes. They did more work by having more amps, having a higher speed, having more flow. Cool? And by the way, we typically call that the watt. What? What? Yeah. Correct. Watt. What did you say? You guys have heard of watts, right? You go to search for light bulbs and stuff, it's like 80 watt, 60 watt. The new LEDs will be like, oh, this is a 4 watt that has the light of an 80 watt. Makes sense? Because like the LEDs are much more efficient. LEDs have very low current flow for the similar amount of lumens. That's why LEDs are nice. But the watt is the amount of power. If you have a motor, motors can operate on watts. If you have a heater, let's say you're trying to make heater, it's nice and warm in here now. If you have a heater, maybe too warm for my taste, but if you have a heater and it's 1,000 watts, you're expecting that to be able to heat like a space like this. But if it's a heater with 12,000 watts, it's going to heat like a small house. If you have a heater with 36,000 watts, that's going to be like a lot, more, right? More energy. You'd expect not necessarily to have a hotter temperature, but a bigger area that it can heat. Cool? So watts is the amount of work. Make sense? The watts of those two people we talked about, one of them did 60 boxes worth of watts, and one did 120 boxes worth of watts. Make sense? Now, how do we produce a watt? 1 watt is produced when 1 volt causes 1 amp of current to flow. Ooh, yet another thing that makes sense in this brilliantly designed scientific universe. The power equation, P, which is the power, equals V times A. Okay, it's that simple. P equals V times A. Not complicated like E equals MC squared. Just simple. Power equals volts times amps. Cool? You think you can do that? How many volts was that last system we talked about?
24.
We had 12, we had 24, right? Let's make it the 12 for now. If we had the 12 and it moved 6 amps, that'd be 12 times 6. But if we had the 24 and 6 amps, that'd be 24 times 6. That'd be double the work. Make sense? Cool? All right, so continuing more with power. Here's the power is more like a formula for you. Okay, in this case, we have a 12 volt system. We have a 2 amp flow through the circuit. So we would do, if you look, P, A, V. P equals amps of 2 times volts of 12. How many watts?
24.
Definitely look at a nice 24 watt system. Cool. 24 watts, not a real big deal. How could we increase the watts? What do you do? You could add volts, that's true. In a car, we generally don't, but you could. That's true. What could we also do? More amps. So if you do more amps or more volts, you get more watts, more power. And that's why it's power. Just barely close it. Perfect. Okay? So, kind of simple, not that hard. You want to do some practice calculations? Just remember the Watt's Law triangle. Yeah, actually, we'll do it right here together. Alrighty, let's go with let's keep the 12 volt system, cool, but let's go with 4 amps. What do we have? 4 times 12 equals 48 watts. Okay, does that make sense? So you went from a 24 watt system to a 48 watt system. You doubled. How did you double? You doubled the amps. You doubled the amps, right? It's once again, it's not really a guess. It's like it's a formula, you know. Cool. And so let's say we did 1 amp already right off the bat. Don't cheat. What do you think the power is going to do? You had 2 amps, now you go to 1 amp, that's less current flow, right? Power is going to go down. All right, do the math. 1 times 12 equals a 12 watt system. 12 watts of power. That's going to be somebody who's pretty slow at stacking boxes. If you want a lot of work done, you need a lot of power. You want to get a lot of power, you need either somebody who has very strong or very fast. You pick which one you want. You want somebody who can take 4 boxes at a time, or somebody who can only hold 1 box at a time, but they're like, I don't know which one's going to win. Maybe we could have to do the calculation.
Second one's probably a little safer.
I think the first one.
Maybe.
Get more done.
Maybe. But what if? So we'll do a formula right now on that fun little test. Let's do the slow one that double stacks the boxes. They're moving pretty slow at 1 amp, but let's say they're not carrying 1 box, they're carrying 4. That would be 4 times the strength. It wouldn't be 12. What would it be? It'd be 48. So if you were to go to a 48 volts, what's 1 amp times 48 volts equals 48 watts. Cool. Now let's just say you have, I'll change colors. Let's just say you have somebody who's really fast, like rather than 2 amps, they're going to do double the speed, 4 amps. Cool. And but you want to have them be 12 volts, or you want to have them be 6?
It's 12. 6.
All right, let's do 12. Exactly. Let's keep it at 12. So their average strength, they could do 1 box at a time, 12 volts worth of power, 12 volts worth of potential, but they move really fast, 4 amps. So we do a 4 times a 12, which equals a 48 watts. They're going to be dead tied. Not M.
So have them fight to the death to your own spec.
Well, it's not like a full-on, like, it's not like that type of competition. It was a friendly competition. You know, saying, hey, who gets more boxes done, big slow guy or fast little guy? Maybe about the same. Maybe the same. Cool. Inspired. However, what if this is not the optimal employee? What if you had a big, weak guy? That would be still doing 1 amp,
Slower.
but only 12 volts. Is this the employee that you want stacking boxes?
No.
So they've got a 1 amp times a 12 volts, average strength but slow, only 12 watts. So that would be only 12 boxes per hour or whatever the number. Makes sense? So kind of depends on what we're trying to do. That's how you calculate power. Any questions?
So,
Also not complicated at all. Definitely not complicated. Cool. Bada bing, bada boom. How you doing? Okay, let's talk about that. And then another way to calculate that for the record would be power is E times R. E being that electromotive force, that's pretty much volts, and then I being amps. Remember, so this is just showing you another way to do the calculation with the other letters. So if you see something like, you could also get this one tattooed. You could have one in here and one in here. Right. It also doesn't help if it's a face tattoo because you can't see it. Unless you'd be like, let me get my phone out real quick. In which case, I think you'd want to put them in mirror so you could see it on the phone. I probably just wouldn't recommend it.
So
Probably not a great
So
idea.
the REWOB.
What?
Yeah,
OU 812?
No, REW because you have to look.
OU 812? What was it? All right, here is the power from like a visual. The battery, 12 volts, right? Got a fuse, got this bulb. If you have a current of 200 milliamps, which there's quite a bit of lessons right there. We talked just a tiny bit about kilo being 1,000. Milli is 1,000th, right? So like how a kilo is 1,000 of whatever it is. All right, I already know you people. Grams, right? If you have a gram of medicine, of vitamins, something, and then you have a kilogram, you have 1,000 of those, right? But what if you have a milligram? That's like a normal dosage. That's like one 1,000th. 1,000 milligrams equals a gram, and 1,000 grams equals a kilogram. Cool? So just 200 milliamps. Let me explain that to you. 200 milliamps, got a decimal right here. If you want to make it amps, you bring it over here. That's 0.2 amps. 0.2 amps is 200 milliamps. This is a pretty common amount of current flow in an automotive system. So if we were to have, and that's how it says 200 milliamps, but look down here it says 0.2 amps. By the way, on the ASE, they'll shoot stuff like this out there, and all you're really knowing is the calculation between kilo to base number to milli, right? They'll be like, oh, this thing has a spec of 1 to 2 kilo ohms, and you're like, what? There is no answer like that, and it'll say 1,000 to 2,000 ohms. That's the same number. 0.2 amps and 200 milliamps is the same number. Who in their pocket's got $1? Who in their pocket's got 100 cents? You have the same amount of money. Don't you dare try to hand me no 100 pennies. Ruin my belt. But it's the same amount of money though, technically. Make sense? 200 milliamps, we just changed that to 0.2 ohms so that way, the math, if you're trying to find watts, not milliwatts or kilowatts, right? You need to get them all to be the base number, which is no prefix, no kilo, no milli. Make sense? No centi. So we took 200 milliamps, we're like, no, forget the milliamps, move the decimal 3 times, 0.2 amps, plug that one in, 12 volts times 0.2 amps equals 2.4 watts. That's how they calculated this 2.4 watt, very, very small circuit. Cool? Like it, love it? Okay, and then I jumped the gun a bit, but we'll do this together with some new numbers. This is kind of what we talked about. If you know 2, you can find the third, but in this case we'll switch it up just a bit. If you had, let's say you knew 5 amps and 12 volts, you could do 12 times 5 and you get 60, right? But the other is true too. Let's just say you didn't know how many amps it was. You have a 60, you have a 12. Interesting. Anybody know what 60 divided by 12 is? Oh, it's 5. Like, whoa. Okay, so it's just showing you this triangle, the top being P, this being A, and this being V. You can figure it out. This just like Ohm's law. It's very similar to Ohm's law. Cool. Now why? Well, let's say you had a 12-volt circuit and you had a 5 amps on this bulb. How many watts is this? Is like a, this looks like maybe a HID or something. How many watts is that bulb? Anybody tell?
60.
Bingo. And that was the answer. You got it. How did we figure that out? Here we go. We had 12 volts and we had how many amps? 5. So we're going to do 5 times 12. That's a 2. 12 equals, and it's 5 amps, right? Times 12 volts equals the 60 watts. That's how you determine the bulb wattage. Let's do it in a different way. We have a 60 watt bulb on a 12 volt system. How many amps does it pull? Here's the calculation. You don't know the amps, cover it up. 60 over 12. 60 divided by 12 equals
5.
Hey, wait a minute, we did this one, but we're writing it out. Equals 5 amps.
Oh yeah, I think you did this one.
Yeah, we did, I know that. So watts divided by volts, right? So if you follow along in the book, it gives you a lot of formulas. It's like, oh, to determine amps, you do watts divided by volts. And to determine volts, you do watts divided by amps. And to determine watts, you do amps times volt. Like, there's 3 formulas, but you know what I like? I like to get this tattoo here. And then you just cover up the one you don't know.
We get extra credit if we get a tattoo.
I ain't paying for no tattoo. Extra credit, yeah, that might be fun. No.
No.
One
Then
point.
it's permanent.
Yeah, it is permanent. You know what I would do? I'd get it right here, so when you get old, you can do this. That's what I would do myself, personally. You'd end up with, your calculation would look like this. Ready? P, A, V, and it'd look like this. You'd be like, dang, and this line's all sorts of messed up. I'm like, look at this, it was cool when I was young. Makes sense? You want to do one more just for fun with new numbers? We'll do it. We could do it on the tattooed elderly version if you want. I'll get you a senior citizen discount though, I think. Okay, let's say we've got, all right, here's a cool application. Remember we're talking a lot about the 12 volt system, right? Let's say you don't know the volts. Let's just say you need a 60 watt circuit, cool. That's the 60 watt, same amount of light as the old one, but you only want to run, let's say, a 2.5 amps. Wouldn't it be kind of nice to be able to run a 2.5 amps?
Yes.
Because you used to need 5 amps, which is a bigger wire. Now if you're going to run 2.5, you could run a smaller wire, right? Doesn't that save money on the copper, the wire cost, right? Cool. How could we make 60 watts with only 2.5 amps? Well, let's do the math. It's 60 divided by 2.5, and we come up with, anybody know?
24.
How did you know? It's brilliant, brilliant mind back there. If we went to a 24 volt system, you could get the same amount of power with half the amps. Make sense? What if we were to go to a 48 volt system? You could actually get this down to what, like a 0.75 amps. You could do like 1 amp to run that HID. See, so like that's why the higher the voltage, the lower the amps, that means smaller the wires. The only, like I said, the negative would be it'd have more electrical pressure. Generally, you're totally chilling, 12, 24, 36 volts. If you start to go to 48 volts, that's when we start to call that like a medium voltage. That's when we start to have a little bit of warnings and a little like a, hey, you should power the system down. 12 volts, you could be like this, like, nothing. 12 volts just not enough. 48 volts, you might be like, oh, how you doing? Like that. Makes sense? So that'd be the negative of the higher voltage system. But the positive would be smaller wires, less amps. Be kind of nice. Kind of cool. If you feel like you need one more, you're good. Kind of similar to Ohm's law. Want to do one more? Feel like you're good. Good?
Okay, we'll roll it.
I believe that. That doesn't sound like an EV out there, does it? Alright, cool. Now, I'm gonna give you guys a couple options. Who can time check for me? Do you want to take a little break now, or you want to keep rolling and take the break later? Give me feedback. You want to go a little further? Okay. All right. Circuits. Circuits. Starting with series circuits. I gave you a preview on this, remember? It's one path. In a series circuit, there's only one path for current to flow. All the electrons flow at the same rate throughout all the parts of the circuit, and the current is the same everywhere within a circuit. Let's make this about traffic. If there's only one road, and the front car is doing 10, what speed you doing?
15.
If you're doing 5, then the cars behind you are doing 5. So whoever's the front, I like that point, but I got a little rebuttal for you here. If the front car is doing 10 and you're doing 5, that front car's gone and now you're the front car. So what's everybody doing now? 5, whatever you're doing. You can't, there's no passing. There's only one path. In the series circuit, the amps is the same everywhere. Make sense? There's only one path. There's no like, oh, let me go around them in the right lane on the shoulder. You know, there's that not only is that illegal, in this it's impossible in a series. Just okay, cool. Kind of visualize it now. But more from an electrical standpoint, all the electrons are flowing in a line, in series like this, all doing the same speed, same amps. Cool. Here's an example. We got a 12-volt battery, and just for the record, the total circuit resistance is 12 ohms. The actual amperage is going to be 1. That's going to be a marching series of electrons. There's going to be 1 amp right here moving, right? Do you remember the amperage is the amount of current flow, right? So 1 amp means 1 amp of electrons here. How many electrons are passing through here? Still 1 amp. Not volts, amps. In a series circuit, the amperage is all the same. Now the voltage can vary, yes, but the amperage is the same. Okay, let's make it the cars again. The front car is somewhere over here. I promise you, they're all going 1 amp. Everybody's going 1 amp. Make sense? They may have different potential, but they're all actually doing 1 amp of speed. You can't, remember the different boxes we talked about power, the one who's fast? Doesn't matter. If the one who's fast is stuck behind a slow person, it's 1 amp. Done, period. No change. Cool. So now, and you see in this one, it's showing you, to measure the amperage, you got to break the circuit open and send it through your meter, right? So if we were to do that, we'd be like, oh, there's 1 amp before the bulb, there's 1 amp after the bulb, there's 1 amp after the bulb, there's just 1 amp everywhere. It's all the same in a series circuit. Cool. And then let's say we had unequal bulbs. Even if this one has more resistance and less, it's all still 1 amp because the front car is leading the way. Basically, they're all in a line. That's when you think a series, you want to think they're all in a line. Amperage is the same. Now, I'll agree with you, though, the voltage is different, but this starts to cross into Unit 3, the next unit, where we're like more about meter usage, you know? So technically, you'd actually have varying voltages, which I've previewed you a bit. But this is slightly difficult to figure out. Let me think about this. It's 3 times the size. If you had a 12-volt system, this one being a third of that size, I believe is going to drop 4. This one's going to drop 8. No, it's not. This one's going to drop 3, and this one's going to drop 9, actually, yeah. So the ohms is the varying resistance. That would tell you how much voltage each one will consume, but the amps in this circuit will be the same. So we're focused on amps right now. Kinda? Series, get it? Okay. And then again, even if in a series circuit, even if there's more than one resistance, those resistances are connected one after the other. The total resistance is the sum of all the individual resistances. back it up. What did you just say? Okay. Look it. We can even do math. You like math. I know you do. Ohm's law, remember? You guys remember who got the tattoo? Did anybody get the tattoo? You want to do it over here? What's on the top? Do you remember?
Volts.
V
Resistance.
R is over here, close. Amps is over here, good, okay? So the total circuit voltage is 12. We agreed 12, right? So I'll even do it right here in a small scale. V, A, R. The voltage is what? 12, right? Now, how do we determine the total circuit resistance? Is it 3 or is it 9?
Times.
Plus 3 plus 9 equals
12.
12, exactly. 12, okay, so the total resistance is all the resistors added up. In this case, it's only 2. But if you had 3, it'd be 3 of them added. You have to add it all. All of it gets added up. All right, so if we have 12 volts and 12 ohms, we're going to do this. 12 divided by 12 equals how many amps? 1. But wait a minute, we knew that already. Huh? Do you see how that makes sense? Yes? Okay, that's how series circuits work. That's not how parallel circuits work, but I've got to get to that point first. Cool. Now, so we agreed on this, we just proved it. However, the voltage at different points within the circuit changes. Say, what? Okay, I'll come back to that. At each point in the circuit where the current flows through a resistance, a drop in voltage occurs, known as voltage drops. Ooh. So that's kind of like the toll. Remember, the parents hand down the money, and if there's one load, the one child gets all 12. But if there's 2, they got to split it, and it's always split proportionally to their strength, which is going to be resistance in this case. All right, kind of picking up what I'm putting down. For the record, voltage drops are good when they occur inside of an intended load. So for example, if we're dropping voltage inside a bulb, that's a good thing. It's going to go. If you listen, you'll hear it, but you might only see it, unless you're special. That's why I make the sound. They're going to cause a good thing, but they cause undesirable effects when they occur where they're not wanted. Remember that toll bridge, that switch? Remember there was a voltage drop there? See, we're not trying to spend $1.30 getting across the bridge, and then we got only 11 something to spend in the restaurant or something. Right? The bulb is the load in that circuit. Now we'll back it up. To this one visually, and then we'll move to the next one. So what we were saying on this one is we shouldn't have a voltage drop on the wire. We shouldn't have a voltage drop on the fuse. We shouldn't have a voltage drop on the switch. We should have a voltage drop in this first bulb, and we should have a voltage drop on that second bulb. This circuit, basically, parents are handing down $12. The 3-year-old is going to take a quantity, and the 9-year-old is going to take a quantity. Who do you think's most strong?
The 9-year-old.
I would say so. So you basically have a 9-year-old that's 3 times the age and 3 times the size. So guess what? It's going to take 3 times the dollar amount. Make sense? They're always going to take as much as they can, dependent on their size. This one's 9. This one's 3. There's $12. Who gets how much? Can you figure that out?
The 9-year-old gets more than the.
Definitely more, but how much more? So then it's kind of weird to think about this. You've only got 12, and it's got to be proportional. The reason that this one's a great example is because you have 3 ohms and 9 ohms. So this one's 3 times the size. So I can just fudge some numbers in there real quick, and I could say, well, what if this one took 3 volts? And what if this one took 9 volts? Does that equal the full amount?
Yes.
It does, and that happens to be right. And the way that that makes sense is this one's 3 times the size, it took 3 times the money. 3, 6, 9, 3 times the money. 1/3 of the money, 3 times the money. However, all $12 were spent. Make sense? It's always going to be a proportion like that. That's another law that we're going to discuss. Cool? So in this case, 1 amp all the way through, yes, but the amount of voltage started as 12. If this dropped 3, how much money's left? So it was 12, 12, 12, 12, 12, 12, 12, 12, 12. 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9. How much after the 9? 0, 0, 0, 0, 0, 0, 0. That would be a good working circuit. Make sense? But if we had, let's say, a problem, I'll give you a fake problem. If this, let's just say somebody put in the wrong bulb and this one became a 9 ohm and that one's a 9 ohm, now what do you think is going to happen? They're twins. They're both 9. It wouldn't blow a fuse because think about a fuse. A fuse is due to excessive current. We just added resistance. So if we were to do the Ohm's law, V, A, R, I had, remember 12 volts, I had a resistance before of 9, 10, 11, 12, but now I have how much? 18, right? So now we do 12 divided by 18. Anybody know what that number is? It's less than 1. Make me get the calculator.
1.5?
No, not 18 divided by 12.
Sorry, I did the other way.
Specifically 12 divided by 18.
0.6, and then it just goes on.
Exactly. 666 number, man. You guys picked a real winner. Alright, so if we were to do this number, this equals 0.667. I'm going to make it better. Amps. So it had 1 amp of current, right? Do you agree?
Yes.
But now it has 0.66 amps of current. Is that going to blow a fuse?
No.
Quite the opposite. See, and that's where Ohm's law will help you to really comprehend a problem. If you added resistance, you lowered the amps. Cool?
That cause the lights to go dimmer.
Bingo. That's going to be the customer concern. This light should be looking really good, but now instead of this one only taking 3 and this one getting 9, it's like, hey, if you were to do this proportion, what do you think how many volts would each one take?
6.
Think, we got $12 and we got twins. They're going to split the money.
6.
6, this is going to drop 6 volts, and this is going to drop 6 volts. But see, it would be happy if it was running on 9 volts with a full amp, but instead it's only getting 6 volts available, and it's down to 0.667 amps. That bulb is not going to be quite as happy. You're like, oh, I miss when I had a little brother and I could take most of the money for myself. Now I got to split it, because I got a twin. I don't know how that happens, but just follow me. All right. Maybe from I don't know. It's a different family. Okay. But let's just say they're the same age and strength. Now they're splitting the money. Make sense? Cool. So that's how it actually works. If you were to measure this, you have 12 volts, 12 volts, 12 volts, 12 volts, 12 volts. You drop to 6, and right here you have 6 volts, 6 volts, 6 volts, 6 volts, and then you drop to 0. Right? So that circuit wouldn't actually function as intended. And that's because there's unwanted resistance here. Make sense? That would be the effect. No blown fuse, but dim bulbs. Okay? Cool. And don't worry, we're going to do lots of these types of experiments, but we're trying to get this stuff in your mind for now. So, if we were to look at this one, this is a series circuit, so this would be series circuit calculation. This one doesn't have bulbs, it just has generic resistors. You don't know what these loads are, but there's some sort of resistor. 4 ohms, 4 ohms, 4 ohms. That's kind of interesting. Here's how we do the math. The resistance, you see this right here? This is resistance total. See that little T? Total resistance, we need to know to plug into Ohm's law, but how you come up with the total is resistor 1 plus resistor 2 plus resistor 3. Resistor 1's how much?
4.
How do you know? Yeah.
As it says.
Yeah. What's resistor 2?
4.
And 3? So the total, 4 plus 4 plus 4? 12. Make sense? So if you want to calculate Ohm's law on a circuit with multiple loads, you have to add them all together. Make sense? That's how that's going to work.
So basically, from point to point, whatever the resistors are in the middle, you just add them.
Pretty much, yeah. You're gonna when you're looking at the total resistance, think of it as here's your total path.
Yeah.
You're gonna start here. I actually did this a little backwards. I don't know. My natural thing is to go clockwise, but you're gonna start here and you'd be like, all right, what obstacles am I gonna face on the way of the entire journey? That's gonna determine my speed. You're gonna see, oh, here's an obstacle, and here's an obstacle. Add this plus this plus this. That's gonna tell you how long it's gonna take or like what your speed's gonna be. Make sense? So if there's one traffic jam, that might tell you, oh, this is gonna take me this much time. But you need to know all the traffic jams on the whole trip to know what the overall resistance is gonna be. Make sense? And what the overall resistance is kind of like the overall traffic. What the overall traffic jams are gonna be is gonna tell you basically your average speed, which equals how much time. Cool? Yeah, kinda. A little bit. So let's do the math. 12 volts, 12 ohms, 1 amp. Am I right? Cool? Alright, what if I were to throw you for a loop? What if I added another 4 ohm resistor right there on the switch that wasn't supposed to occur? Remember, now this switch has taken its toll. It's not supposed to cost us much, but now it is. What's the total resistance?
16.
16, yeah. 4 is 12, plus another 4 is 16. Now we do this, 12, we do 16 ohms. If I just increase the ohms, the guy with the rope is pulling harder, what's the amps?
Decreases?
It's definitely going to decrease, I agree. But how much? I don't know. Let me see if I can get that calculator out.
0.75.
Yeah, that might be right. See, for some reason I can't pull the calculator up like that. Let me pull it up this way. Okay, how do we do that number again? It was 12 divided by 16. Your amps is going to be exactly what Mason said. 0.75, so your amps went down. Slower traffic, right? You're like, oh, there's 3 car accidents, plus I got to wait for the toll bridge now. And that also means all of these are not going to be kind of unhappy because they were going to take 4 volts, 4 volts, 4 volts, right? Because it's going to always equal 12. All the loads will always drop the full source amount. The source amount is 12. This was going to go, now you got triplets. I'm going to be like, I'll take my 4 volts. I'll take my 4 volts. I'll take my 4 volts. So in a good working circuit, you'd have 12, 12, 12, 12, 12. 8, 8, 8, 8, 4, 4, 4, 4, 0. Cool? That's how it should be. But now instead, we snuck a little extra resistance in there because we have bad contactors in the switch or corrosion or whatever. And now it's like 12, 12, 12, 12, 12. How much is it going to drop here? Well, that depends. It's not necessarily going to drop 4 volts because look, we only have $12. And $12 got to be split not 3 ways, but 4. So you'd have to go like a 12 divided by a 4 equals 3. So this is going to take 3 volts. So you start out with 12. By the time it goes through this unintended resistance, what do we end up with? 9, 9, 9, 9. What about this? 6, 6. What about this? 3, 3. What about after? 0. Okay, that's actually what the voltage is going to do. Make sense? Your amperage goes down, yes, but your voltage can change depending on the resistance throughout the circuit. Starting to get it? It's abstract.
To determine your resistance, because it's not always going to be 4, 4, 4. It's going to be like, let's say like 2, 1, or 3.
Yes, and that's true. And we're actually going to cover that. That's a different calculation, so that's coming. Promise you it's coming. But you're right. The gist of it is though, just make sure you understand if the resistance goes up, the amps goes down. Right? And then now a little bit less about the Ohm's law and the math and stuff, just overall about the circuit. Here's your source. Here's your wires. This is the protection device. What's that mean? Fuse, yeah, generally. And you know, some things it could be a circuit breaker. Circuit breaker is like a fuse, except you can reset it. You don't have to replace it. What the heck is a control device?
Switch.
Yeah, like generally gonna be a switch. It could be a number of different types of switches, but maybe this is the door jamb switch or the headlight switch or the power button to the radio or something. Then there's gonna be the load. Give me an example of what the load could be.
A light.
A bulb, what else?
The starter.
A motor, yeah. Maybe even electromagnet that moves something, such as a solenoid or something. We're going to come back to circuits, to components, but this is your basic circuit. The path should go positive out, protected, controlled, load, ground. So if this is a well-functioning circuit, if you're picking up kind of like the voltagey stuff, if this battery has a 12-volt potential, we should have 12 volts here. What should we have at the fuse?
12.
What should we have after the fuse?
12.
Should still be 12, but you know what happens if the fuse is blown?
Nothing.
0. So you could measure that right there and be like, hey, I have 12 going in, I have 0 coming out, the open's right there. Bada bing, bada boom, how you doing? That's how you get a new fuse. So if you see somebody pulling fuses out and holding them up to the light like this, it's just because they probably don't really know how to do this the professional way. Does it work? Yes. Did my dad hand me a fuse last night to have me check it? Yes. Did it kind of bother me? Yes. I'm like, Dad, just leave it in. Let's test it. And he's like, pull this one out, pull this one out, pull this one out. I'm like just leave them in there, stop. You know? So that's how you do it when you don't know. But when you know, you can measure it, right? Just like what we said, 12. If you have 12 going in, 12 coming out, the fuse is good. Leave it in the fuse box. Don't hand it to me, Dad. I don't want it. Just let me check it. He's a body man. He can make the car straight. But troubleshooting, that's my thing. Then the control device. So if let's say this is good, cool. We should have 12 going into the switch, right? This switch is open. This 12 volts should make it right to that point, and it shouldn't go any further. So what should we have coming out? 0. And that's normal, by the way. But what if we close the switch? What should we have coming out?
12.
Bingo! And then that means this bulb should get 12, and coming out should get, it should pretty much be 0, yeah, exactly. Now, in the series circuit like we talked about, if we were to accidentally add a little resistor right here, and let's just say this was a 4 ohm, and there was 4 ohms of unintended resistance, how much do you think would be right there? You want it to be 0.
8.
There's 4. Okay, if this one's 4 and this one's 4, now it's almost like there's 2 loads in the circuit. Remember, there's $12. This is 4 and this is 4, so how much does this one take? Yes, if you have 6 volts on the ground, that means you have an equal amount of resistance somewhere on the ground side. And that could be the mouse chewing. Right, but you might be looking over here. It ain't over here. You know because you measured it. There were 6 volts on the ground side. You know it's somewhere between here and here. If you didn't get it, that's normal. We'll get there.
That causes the light to be dim as well.
Exactly. Whether the added resistance is here or here, remember, it's a series circuit. It's still going to lower the amps, and that bulb is still going to be dim because it's sharing the allowance money. Make sense? Cool. All right, that's kind of a little bit about the circuit. I promise you we're going to come back to a lot of that. Predicting voltage is actually what we focus on mostly next week, but I gave you a little bit. I want you to chew on it. And then next week you'll hopefully kind of have it, and then we'll really strengthen it. Cool. All right, so the series circuit's laws are current flow stays the same in all parts. The voltage drops as the current goes through. The resistance is in series. The applied voltage is equal to the sum of the individual voltage drops. This is called Kirchhoff's law. So that's the allowance thing I was saying. Is like, if the parents hand down $12, trust me, all that $12 is going to get used up. Each load is going to take some of it, but the amount it takes or consumes is going to be dependent on its resistance. Cool, but it's always going to use it all up. So that's Kirchhoff's law. We're going to cover that. And the resistance, you add them up in series. So a series is just this resistor plus all the resistors added together become the total resistance. Cool, those are the laws. Kind of makes sense so far? Here you go, like for this one, there's two loads here. So the total resistance is this one plus this one. Now, if there's unintended resistance here too, we got to add that too, but there shouldn't be resistance there. So we're focusing mainly on how it should be more so than, you know, all the potential failures, because there are several. Okay. Cool. And then just to re-summarize the voltage, remember, the voltage is going to vary throughout the circuit depending on where the resistance is. So if there's two resistors here, some of it's going to be spent here and some of it's going to be held over and then later spent right here. But the amount it loses in voltage drop is going to be dependent on these individual resistors' resistance. Kirchhoff's law. Right? Now, this one is just like kind of showing you, if you were to check the resistance all the way down, you'd likely find a little bit of voltage spent in various points. So like this fuse, you know, it might have a tiny bit of resistance. So right here you spent 0.1. If that's dollars and cents, that's 10 cents. Yeah, you lost 10 cents going through the fuse. You lost 10 cents going through the switch. This one happens to have a dimmer. So you've seen the lights where you can make them bright or dim? Mm-hmm. Now I'm going to blow your mind on how. If the dimmer is a resistor, which is kind of like a load, but it's not a load that gives light, it's just resistance that varies, you can change it. So if you turn the dimmer all the way up, that's like no resistance. The light's going to be what?
Right.
Full bright. But if you turn the dimmer down, maybe because, you know, Valentine's Day is coming up. By the way, that's a holiday for the school. They're considering it some sort of weird President's Day celebration. And I'm like, yeah, that's definitely Valentine's Day. But, however, if you turn it all the way dim, that's going to increase the resistance right here, and that's going to consume maybe 11 volts, and that's only going to leave 1 volt for the lamp. And what are the lamps going to be? Dim. Like a candlelight type of, no? Maybe? I don't know. But that's how the dimmer works. The dimmer is just a variable resistor. Sometimes we'll call it a rheostat. Cool. So we have a resistor here, and we have the actual load we're intending. This one dropped 4.7. It left 7 volts for the lamp, for the lights. And then you have just a small drop of voltage on the ground. This one kind of tends to hit a little over the head, but we're going to come back to this next week, and you're going to be like measuring this on the board. Actually, we're going to set some board stuff up today, build some circuits, but you're going to do the actual measurements starting next week. This one, if you get this, you're in really good shape. If you don't, not a real big deal, but you can see what we do with the meter. We take measurements. This meter is measuring the difference in pressure from before the dimmer to after the dimmer, and it's saying, hey, you dropped 4.7 volts right there. You're like, oh, okay. That could be good. Now, if I turn it down and I turn it up, that number should change. That's how we can test the dimmer. See if the dimmer's good or the dimmer's bad. And then, again, available voltage is another way to test it. So right here, Arleth, can you see my battery percentage? Or not really?
It doesn't say.
Okay, we'll roll it. Right here, if you could understand this, you'll be really good. So I'm just going to give it to you like as a basic. Right here, we're measuring the available voltage. We had 12, then we had 11.9. How much dropped? 0.1. Hold that thought. This one's saying if you measure before and after, the meter reads 0.1. If you don't want to do that, cool. You can measure available voltage. You can just slam this negative on the ground, this black terminal on the ground, and poke it and be like, there's 12, then there's 11.9. It dropped 0.1, right? Mm. If you want to do it as a voltage drop, you would do it like this. Put the red one here, put the black one here. In fact, I could do it with, I will become the meter leads for you. If I don't throw things across the floor. right here, if I take my meter and I do this, it will read 0.1, okay? It will read 0.1. It will read 4.7. Or I can do this, shove this on the ground, it'll read 12. It'll read 11.9. It'll read 11.8. How much did I drop here? 0.1. How much did I drop here? 0.1. If I went from 11.8 to 7.1, how much did I drop?
4.7.
It's the same as on the other video right there. There you go, right? So 2 different ways to measure voltage. This one we consider available voltage. How much is available here? How many dollars you got, mom and dad? 12? After the switch, $11.90. After the fuse, $11.90. After the switch, $11.80. After this pesky brother of mine, $7.10, right? It's just, the available voltage tends to be the first thing we do. But so you know, when you hear the term voltage drop, you could also say, how much did brother take? Boom! Brother took 4.7. $4.70.
So you gotta keep his ass.
I'm gonna try, but the problem is, as you can see, I'm only slightly larger. So I'm gonna try. I'm gonna win, but I'm gonna take some punches. These are kind of similar, right? Mason, kind of get it. It's tough, but next week for sure. Okay, and then when we talk about this term, predicting voltage drop and available voltage, that's when you guys are just gonna be able to look at a circuit and trace it out and predict, okay, here I should have about 12, there I should have maybe a little under, right here I'm gonna drop a certain amount, right? You could trace this out. I would go like red, I'd probably change right here to blue, probably change right here to green. You wanna do that to get it straight in your mind, what should be occurring in the circuit. It's very difficult to walk up to a car and be like, what voltage should be available here? They don't tell you that. They give you the circuit, you have to read the circuit, understand a little bit of Ohm's law, but also Kirchhoff's law, and also like symbols, right? So we're gonna go over all these things. Within 3 weeks, you should be able to trace this out and predict the voltages. If you can do that, you're one step away from going over to the car and diagnosing it. Really, that's it. You give me a diagram, if I'm like, okay, let me look at the diagram, yeah. This should all be 12, this should be a little less, and this should be 0. Boom, I go over, I could do a couple tests, and I can tell, is the problem up here, is the problem in here, is the problem down there. That's the direction we're going. But nobody's quite ready for that yet. Okay, so just giving you a sample how that is. Then if you want to measure the current, this is the chicken and the egg thing. I want to show you how to use the meter, but I need you to understand the electrical theory and Ohm's law first. But I still want you to sort of understand the meter as it's related to Ohm's law. So I'm sneaking a little in there. If you want to measure amps, you got to open the circuit and you got to insert it, because now the electrons come down, they go through the meter. The meter counts the number of electrons, shows that number on screen, and then they continue and go in. If you measure amps, don't forget, you got to open the circuit. They call this placing the meter in series. Do you now understand why we call it placing the meter in series? There's only one path. We don't place it in parallel. If this was still connected and you put it here, now you have 2 paths. It could go this way or it could go this way. It'll go right through that meter that would be bad. That'll blow the fuse. So we need to make it go through the load originally by opening the circuit, sending it through, and then allowing it to still go through these loads. Don't give it a second path by parallel. Parallel's next. Yes? No? Definitely yes. Whoops. And then here's your resistance measurement. If you want to measure resistance, cool, but you gotta isolate the component. So if you want to measure resistance of the dimmer, disconnect the dimmer, measure it here, uses its 9-volt battery, determines how difficult it is for the electrons to flow, gives you a reading. Right, so that's how you measure them. Just as a preview, because we're focused on Ohm's law, but understanding it. Now, I think what we should do, let's pause at parallel. All right, so the weight is over, parallel circuits. So lots of words. Then we'll look at pictures. In the parallel circuit, all the components are connected directly to the voltage supply. What the heck does that mean? Well, I'll show you. If any connection or component fails in the parallel circuit, current continues to flow normally through the remaining circuits. And then since all the components are connected directly to the battery terminals, we end up using the ground for the return path. Okay, pause. You guys, it's been a long time since they worked this way, but have you ever seen like a movie or a cartoon where they got a long string of Christmas lights and then they're all out and they're checking one bulb at a time to find the blown bulb? Those are series Christmas lights. That is a horrible, horrible invention. That was a fail. I don't know who came up with that. Somebody needs to go to jail. So if it's a series circuit and one load fails, none of the loads are going to work, right? So if we were to draw it out, which in fact, we could draw it out or I could just back it up. Here's your series circuit. If this bulb blows, they're both out. Makes sense because there's only one path in a series. Cool? One Christmas light blows, they're all out, and then you're there switching the bulbs, trying to figure it out. By the way, you don't need to switch the bulbs, you could just measure it. But you have to know how to measure it. To do that, and I would start right at the middle and determine if it's over here or over here. And if it's over here, then I'd split that in half, and I'd measure this way. And if it's over here, then I'd go to the middle and right, so that's the half method. That's how you professionally would diagnose where the open is if it was in series. All right, but the parallel is a little different. When we're in a parallel, what this is kind of saying is, if a component fails, current continues to flow normally through the remaining circuits. I got that. Here you go. If it's series, remember if one bulb blows, the whole thing is out, right? In parallel, if this bulb blows, guess what? This one still works. So that's a big benefit because, you know, sometimes we have things like Christmas lights and a bulb blows. You don't want to lose them all. It's okay to have one bulb go out and then you can, you know, still have Christmas lights. So look at the parallel right here. The battery goes to here, out, and out. So do you see how both of these bulbs have connection to the power source? You agree with me, right? They both have their own individual connection. Additionally, they both have their own individual grounds. So that's what I was saying, like the ground path is a lot of times the chassis. So we'll just ground this one to the chassis, we'll ground this one to the chassis. We'll send one wire out, make like a splice, send one in and another one in, and you could do it with as many as you want. Cool? Parallel circuit's kind of like how the roads are. If you go down one road and that road is blocked, that's okay, you just do a detour. You'll find your way, right? The electrons, they'll find their way, even if this one's out. They'll find their way. Kind of make sense? Any questions you think on parallel so far? You get me? You can see the difference, right? One path, multiple paths. Because remember, we're going to combine these two in a bit on a series parallel circuit. Go ahead.
Is the ground for the top of that bulb?
Yeah.
Like not connected to the chassis?
Uh-huh.
Would it not light up at all?
If this ground was bad, that light would go out. This light still has its own path, right? So if you visualize it, electrons can go, still works. Electrons will go, but there's no ground, so this won't work. That's kind of cool, huh? So they each have their own independent path. Totally. So if this was your left tail light and this was your right tail light, if your left tail light goes out, your right tail light still works. If your left tail light has a bad ground, your right tail light still works. Make sense? We don't generally put a lot of lights in series because bulbs blow, and when they do, they don't work. The whole circuit won't work, so that'd be kind of unsafe. Cool. And now one more thing I want to point out. Does this section here kind of look like a series, right? There's only one road here, right? Isn't this series? Well, the reason, hey, I don't want the next people to be able to get in or what? Huh? All right. So right here is like a series, but do you know why this is a parallel circuit and not a series parallel? There's no load right here. So a parallel circuit, it still may have only one road, but all the loads have their own individual path. Okay, that was always something that was a little confusing to me. Cool. So as we continue talking about one terminal of the battery and one terminal of each component can be connected anywhere on the body or chassis to complete the circuit, known as common, or like a chassis ground connection. That's really where the ground term comes from. All those loads, if we were to back up, they may have their own individual wires. Technically, they all start here, though, if you think about it. So it is kind of interesting. They all start here. But once they branch out, like maybe in the fuse box, there will be 100 different connections, and they all have their own little wires. Like maybe this wire's red and white, and this wire's red and black, and this wire's red and green, and this wire's red and yellow, right? They'll all have their own individual circuits. But if you look, they share a common ground, which is the chassis. Cool? And that's why sometimes I was saying they'll call it the common. But we don't, in the US, we don't generally say, oh, the common, or like the ground. Cool? So if someone says, oh, check the ground, do you know what they're talking about now? They're talking about, check this. Check this. If they say, if you're working on the left, let's make it, yeah, we could do like left and right. I guess it doesn't matter. Left tail light, right tail light. If you're working on the right tail light and they're like, hey, check the ground, they don't mean check this ground or this ground. Like they're already, you should already understand if this tail light's out, we're only worried about this ground. If this ground was a problem, the whole car wouldn't work. If this ground was a problem, this tail light would be out. You don't need to say which ground. You'd be like, the only ground that's relevant here. Don't be asking me silly questions like that. Cool. So as we continue, in the parallel circuit, the laws are different. That's why we separate them. The voltage across all branches of a parallel circuit are equal. What? How many volts you want to be available at the battery? Positive. 12. So what's available to this bulb?
12.
What's available to this bulb? I want to be a part of that family. I don't want to share no $12. This brother gets $12. This brother gets $12. You get $12. You get $12. See how parallel is kind of different? Parallel gets full access to the cash. They all individually get access to the full 12-volt battery. Make sense? Different though, huh? So that's the first law that's different. Do you remember how parallel is? I mean, how series was? Series, yeah. All of them together get access to the 12. This one doesn't have a direct connection. This one doesn't have a direct connection. They have one $12 coming in. They got to split it up. Make sense? Cool. All right. And then the total current in a parallel circuit equals the sum of the current flowing in each branch. What? All right, so we won't do the math yet. We'll do the math soon. The amount of current in a series is all the same. Remember we had 1 amp flowing? There's 1 amp here, there's 1 amp here, there's 1 amp here, there's 1 amp here. It's all the same. Parallel is different. If we had 1 amp here and we had 1 amp here, how much is here? It's not 1. Think about it like this. Visualize it as cars. Let's say the cars, this is the main road, right? Some cars get off at this exit, some cars get off at this exit. If there's 1 amp worth of cars here and there's 1 amp worth of cars here, how much was there back here before either one got off? 2 amps. So you have double the cars. Some half go here and half go here. There's 1 amp of cars here, there's 1 amp of cars here. There must have been 2 back there. So the amperage quantity is different at different points in a parallel. See how that's so different? Totally different. Make sense so far? All right, cool. Now, the total resistance of a parallel circuit decreases as more branches are added. What? Okay. And the parallel circuit resistance will always be less than the lowest branch. I'm gonna explain that just physically, and then we'll look at it mathematically. All right, right here, the more bulbs we added, these were all resistors when we were on series, right? More resistance, more resistance. You get more resistance. You get more. For every bulb that we add, we're just bogging the road down because there's only one road. Now think about what I just said. What if I add another road, and I add another road, and I add another road? Isn't that going to help traffic flow better?
Yeah.
Exactly. So see, I'm not just adding an obstacle, it comes with a road. So even if this obstacle slows you down, it's still another road. So if you have 2 amps right here, and you have 2 different ways, you'd be like, oh, there's an amp worth and there's an amp worth. The resistance is overall less. If this is 4 ohms and this is 4 ohms, it doesn't become 8 ohms. Make sense? Because they're not in series. 4 plus 4 would be 8. In this, it's a different calculation. It's not adding resistance. Every single resistor you add, as long as it's on its own individual path, is less resistance. Here's how that's very relevant. You guys ever seen the like a tractor trailer that's got all sorts of lights, like kind of blinged out? You know what I'm talking about?
Yes.
Like you'll come up on one, it'll be like orange light, orange light, orange light, orange light, orange light, orange, 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 red, 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 red. Like, okay, were they on sale? They must have been on sale. That was like Temu or something. They were cheap. They were like 50 cents. Okay. If it's a series, every light you would add resistance and they all get dim, right? And your amperage would be less and less and less. We don't do those in series. We do those in parallel. So for every bulb you add, I just said the resistance does what every time we add a new path? We're adding a new road. What's the resistance do in a parallel? Total resistance goes down. Here it goes up because you're bogging it down. Here, every load you add comes with a new road, comes with a new road, comes with a new road. If we have 2 right here, there's 2 amps here, but what if I add a third and they're all at 1 amp apiece? How many amps are here now? 3. What if I add a fourth? 4. 5, 6, 7, 8. What if that tractor trailer had a circuit for those lights that was 10 amps and they went and put the 11th light on there?
They busted.
It's going to have too much current flow. It's going to blow the fuse. An old trucker Jim is going to be like, oh, I know what to do. Put a 15 in there. You know? Right? So that's why Ohm's law does matter to you as the technician. If a tractor trailer comes in and you're working on it and they got all sorts of lights all over the place and the 10 amp fuse is blowing and you measure it's pulling 11, 12 amps, it's like, hey dude, you like Timu had a sale or whatever and you added all these lights and stuff. You can't do that on this circuit. This freeway right here is only big enough for 10 amps. You can't handle 11, 12 exits off of that same freeway. Now, if you could only get the local governments to understand these types of things, they would stop adding so much without improving the freeway. I mean, you understand what I'm saying, right? You know, big part, well, you guys don't have it so bad right here, but like Orange County, LA, San Diego, they've added so many side roads off those same freeways. These freeways, they're not made to handle that many cars. And that's why traffic's all jacked up. See how this could be very applicable to other areas. That makes sense? So the trucker is over current on this part of the circuit because they've added so many lights in parallel, not series. Cool? So how that looks a little more mathematically, like it's saying a parallel circuit's voltage across each branch is the same, irrespective of how many branches. Here's what that means. This one gets 12 volts, right? How much does this one get?
12.
So if you add another one, how much does that one get?
12.
Another one? 12. Okay, that's what that's saying. All the branches, all the new load that you added in a parallel would get access to the full 12. Cool? And the current flowing in each branch is determined by the resistance of that branch along with the voltage used by that branch. All right, so like making it simple, if you want to know the current flow right here, you already know it's 12 volts, right? You measure this resistance right here. Remember in Ohm's law, we could do volts, and if you want resistance, it's volts divided by resistance equals amps. So you'd measure the resistance of just right here, and then you'd be like, oh, there's, you know, if it's 12 volts and 12 ohms, there's 1 amp right there, right? If this one has 12 ohms, but this one has 6, do you know how many amps would be right here? We're gonna do the math. You wanna do the math? You basically make it into a mini series, and we do the same thing that we were doing. All right, right here, let's make this a 12 ohm, and this one a 6. So, and right here we have 12 volts. So we'll do the same as right here. V, A, R. In this first one, the volt's 12, right? So we're 12. That's over the resistance. Let's do this one first. 12 over 12 equals how many amps? 1. And that's for this one. For this one, we have 12 volts, 6 ohms. 12 divided by 6 equals how many amps? 12 divided by 6, 6 will go in there 2 times. So you'd have double the amps. Now I heard the 0.5, and that one was actually a really good answer. If it was 6 divided by 12, that would be 0.5, but the way sometimes I double check my math, sometimes I'll switch them up, cool, in full transparency, I will. But how I'll do it is I'll say, wait a minute, I have less resistance here. If I have less resistance, that's this guy, remember? If he's pulling up less on the rope, what's the amperage doing?
Keep going.
More amps, yeah, it doesn't go down when you do less resistance. Cool, so I'll double check myself with logic and be like, nah, I think I did that one backwards. Let me redo it again. I'll tell you dead flat out, my memory for like formulas is horrible. My memory for dates is also horrible. I do know Valentine's Day though. Okay. There's a couple dates I remember, but like if you ask me, hey, what's the holiday? I'm like Veterans Day, Memorial Day. I just don't know. However, I like to keep myself in check, knowing my weakness. I'll keep myself in check with just the logic of, wait a minute, this has less resistance, my amperage should go up, not go down, and then I'll know that I screwed it up. And then I'll do it right. Maybe. Okay, cool. And then look what it says. With the resistances that are not equal, the current divides in accordance with the resistance of each branch, but the total current flow is still the sum of the currents flowing in each other branch. What? Okay. So what I was saying, remember we had 1 amp right here, and what did this one have? 2 amps, right? Those aren't equal. If I have 1 amp and 2 amps, what's that make this one? 3, exactly. That's what all that word's is saying. Cool. Now, here's a fun picture. This is just kind of re-showing what I was saying. But we don't have 2 bulbs, we actually have 3 different resistors. We have a 2 ohm, we have a 6 ohm, we have a 12 ohm. If you were to do the Ohm's law for each, I guess we can do it. There's no reason. Let me see if that first one, come on baby. If you can see that 12. Yeah, you can see the 12 fine. All right, so if we did the individual math for each of these, same thing, 12 over, and we're going to do the R right here. So that's all we really care about. If it's 12 divided by 2, what do we get? Bingo. Do you see how we came up with the 6? Yeah. If it's 12 divided by 6, we get 2. Bingo. If we do 12 divided by the 12, we get the 1. Okay, so when we calculate the resistance, when we want to know the amps here, you just do it as its own individual circuit. You basically do 3 series circuits, and then you can look at it and you can be like, all right, I got 1 amp, I got 2 amps, I got 6 amps. I got 1 car, on this road there's 1 car, on this road there's 2 cars, On this road, there's 6 cars. That means a couple moments ago on the freeway, all those cars were on the freeway. How many was there? 6, 7, 8, 9. Exactly. Now, do you understand why this is a 9? That's just how it works. You know, that's why I like to use cars. It's very visual.
So theoretically, if you use something that had mathematically put in like light bulbs that had different wattages on each
Yes.
one of those wires,
Uh-huh.
you could actually get it to work correctly.
Actually, this would work correctly right now, and the reason why is because this light bulb wants access to 12 volts, and believe me when I tell you, it's got 12 volts. This one's happy, it's got 12 volts. This one's happy, it's got 12 volts. So what's cool about a parallel is they can all work just fine. You can put different size lights. You could do all sorts of stuff in a parallel. If you had different size lights in a series, some of them are going to take too much, some are going to take not enough. You're kind of messing it up. You know, that's generally how it's. We don't really try to add lights in a series circuit. It's just counterintuitive. You may get 2 lights and they're both going to be half dim. So what'd you end up with? The same as the 1 light. You know what I'm saying? So if we're adding paths and we're adding loads, you could do it like this. Like the good example would be that tractor trailer thing. Maybe the tractor trailer is like, hey, I've got all these 12 ohm bulbs and they're not that bright, but I also want to add some brighter ones to make sure people are paying attention. No problem. You can tap in and you can add some 6 ohm bulbs, but you gotta, you know, what you really have to do is just be able to know how many amps on each one of these circuits and make sure it's not going to be too much for this one, because right here is where the fuse is going to be. Fuse is going to be here. And if that fuse is at 10 amp, this system will work. But let's just say we want to add another one right here, and let's make it a 6 ohm. That'd be a fun number. If it's a 6 ohm, how many amps are going to flow? Remember how to do it, right? 12 divided by 6 because of this.
Should be 2.
Okay, that's going to be 2 amps. How many amps are flowing here now? Right, because we just added. We had an amp, 2 amps, 6 amps, and 2 amps. Now additional 11 amps. What's up with our fuse?
Blown.
Zonk. And that's what Timu truck driver did. He just coined his term.
So you would have to make that a 15 amp.
You would, and I'm cool with that. If you want to do a 15 here, yes, but not by pulling this fuse and shoving a new fuse in there. What would you have to do to do it correct?
Why?
Exactly. You'd have to cut this wire out, cut this wire out. Maybe we bump up to a 16. Maybe let me think of the numbers here. A 14 would do 15 amps. Yeah, we could yank this one out and put a 14 AWG, and then you'd be totally legit to bump this up to a 15A. However, what size is your ground wire? Because look, not only was 9 amps, now 11 falling on the positive, that's all going to flow from here to here as well. See, because they're all back down to a freeway right here. So if you're going to upgrade that side, cool, you need to change this wire out to a 14 AWG as well, because a 14 AWG from memory handles 15 amps.
Is that a ground?
Exactly. So this is the ground, but what's a little bit misleading though is it depends on how it's wired. So let's just say I wired it like this. I pulled this over here and I put it on chassis ground. Now they're no longer actually having to travel through this one. They're all going on chassis ground. Think of the wire size like the size of the freeway lanes, right? You only had 2 lanes, but you really need 3 lanes. So you add a 3-lane highway, and now everybody's chilling, and now you're like, the politicians could solve this. It takes taxpayer money, but we're spending on all sorts of dumb stuff anyway. Give me another lane on that freeway. That's what I want. However, there's another way to do it. We could say, you know what? We can have them all go to their own individual chassis ground. The chassis ground is like the biggest freeway you've ever heard of. It's the whole frame. It's not a wire this big. It's like the frame, the body. Like the chassis ground is beautiful. It's only one problem. At the end of the day, the chassis ground has to jump over to the battery terminal, so they usually use a pretty big fat ground that jumps to the frame or to the body off that battery. You ever notice that? You look on your negative terminal of the battery, there it is, and you'll notice it goes somewhere pretty short and grounds out. So ultimately, all the electrons in the whole system all have to use that little battery ground, so you just got to make sure that the negative one is pretty big, pretty rocking. So that's kind of that's how you'd actually design the system to work and not burn to the ground, in case you wanted to know. Now let me skim, yeah, that's what I thought. So we're gonna do a little bit of math on this, because you love it, and you need it. And now hopefully you guys I've sold you on why you need to know Ohm's law at least a bit. You know, if you wanna start doing some customization, you wanna add some lights, you wanna add some whatever, you wanna work on something that's not OEM, you might actually have to do a little bit of figuring here. The next concept is how to calculate the resistance. So here's your formula. Resistance total equals 1 over R1, 1 over R1, 1 over R1. So it depends on how many resistors you have. It's a little bit funky. So if we were to have, in fact, I'm going to need to draw all of this. So let me just get this out of the way. If we were to back up to that formula, or that diagram, we have a 12, a 6, and a 2 ohm, right? A 12, a 6, and a 2. I'm going to do some of this together. R1 was 2 resistors in parallel. Yeah, R1 was a 12, a 6, and a 2. So you'd have to do 1 over 12 plus 1 over 6 plus 1 over 2, get that number, and then put that as 1 over whatever that number is. The math just got a little more complicated, didn't it? This is not something I commonly do, in full transparency, okay? But I want you guys to understand how you would do it. So probably the way I would be a little more tempted to do it is punch these into decimals and probably do the decimals like that. You could also find a calculator and you could run in the calculator. I'd say the main thing you need to know as a technician is every time you add one, this number ends up lower. So if we were to do, let me think, anybody remember how to add fractions? 1, I think it's going to be 12, plus 6 is 18, right? Plus 2 is 20. Is it 1 over 20? I think that's how you do that. I don't exactly remember. I'm struggling to remember this. You gotta find the common denominator, dang it. Well, we could use, I guess what, 12? Okay, 1 over 12 plus, this would become 2 over 12. And this would become, what was this one? 2 would be 6 over 12, because it was a half, right? So it'd be 6, 7, 8, 9, 9 over 12. Yeah, that probably makes more sense. This is not something that we normally do. So, electrical engineers, definitely. If I think about this for a moment, I'll definitely remember it. But let me come back to the other thing we could do that's a little bit more logical is the total resistance equals R1 times R2 over R1 plus R2. So let's just say we took these first two, and let's say it was, what was our numbers? It was 12 ohms. We had a 12 ohms, and the second one was a 6 ohms, and then a 12 plus a 6. So anybody know 12 times 6? Calculate.
42.
Well, hey, it's okay.
72.
You do have the calculator for a good reason.
70.
12 times 6, right? And then, what was the other one? 12 times 6. Well, I need to put the calculator in a slightly different spot. 12 times... I ruined my formula, didn't I? How did I do that? There we go. But now I lost my calculator. Okay, there we go. So this equals 72. And then 12 plus 6, we could do this one. Okay, 12 plus 6 is 18. So we can do 72 divided by 18 is 4. What's our total resistance? 4 ohms. Right, so if we were to look at that circuit, then you would, figure out all the resistors, and you'd notice we had a 12 ohm resistor. This part is a little more normal. So we had a 12 ohm resistor, right? And we had a 6 ohm resistor. But the total resistance will always be less than both of them combined. It's always gonna be less than even the lowest one. Because remember, we added an extra circuit to it. Make sense? So this number makes sense. Even if you thought it was gonna be like 12 plus 6 would be like 18 ohms. No. That would be if it was in series. In parallel, this is the new calculation. So let's say that we were to do these numbers. We would do, remember how there was 3, right? RT equals, rather than doing this way, let's do it like this. 12 times 6, and what was the other one? Times 2 over 12 plus 6 plus 2. Can we do that math? Did we start smart enough? You could probably do it based on what we got right now. 12 times 6 was 72, and then times 2 we're going to double that, but we'll do it the long way. Who knows? Clear. 12 times 6 times 2. 144.
Divided by 20.
And this one is 12 plus 6 is 18. I heard the 20. Plus 2. You following this? 20. Now pause right there. Just stop. Because I'm coming super clean with you. Technicians don't do this math daily. And just so you know, I never pregame before the lecture. I roll it straight up. That way, even if I'm struggling, I'll figure it out with you. I think it helps you more so than make me feel really good about myself. I'm totally cool with that. I have not done this calculation in I can't tell you how long. Because I actually don't normally teach electrical. But I have. The last time I did this calculation was, guess what? Last time I taught electrical. So fixing the cars, we don't really do this. But this is the practical takeaway. If I just added a resistor, remember how I was adding resistors and you're thinking it lowers the total resistance? I just added a resistor of 2 ohms. Do you think this number is going to be higher than this or lower than this?
Higher.
Lower.
We got a disagreement. Let's crunch the numbers. 144 divided by 20.
7.2.
What? Something is wrong there. Did I do that right? I did get a 7.2. That is not correct. How did I get that messed up? 144 divided by 20. I did that correct, didn't I? Yeah. It should be lower. The total resistance should be lower. Interesting.
Run the formula.
Run that formula one more time. I agree. R1 and R2. Let's redo them. 12 times 6, 72. 12 plus 6 is 18. And this one, 16, 17, 18, 20. I'm going to have to pause on that and see why I'm tripping. That number definitely didn't make great sense. Okay, I'll tell you what. In the current day and age, I am okay with cheating on that number. So let's do probably what I would have done in the meantime. Parallel circuit resistance calculator. this tool would be probably decent. Okay, number of resistors. All right, how many do we have on that first one? 2, right? Resistor 1, this is where we were before. Resistor 1 was 12, resistor 2 was 6. Let's check on that. 12, 6, not all that. Calculate 4. Okay, chillin'. We agree on this one. Okay, the other one, we need 3 resistors. So let's bump that up. 3. What was it? 12, 6, and 2. 1.3, but how? Okay.
Is there anywhere where like it's gonna show the full formula so you can kind of visualize it?
I would probably have to study it for a bit, but I have one redeeming thing. When we add another leg of resistance, even though we're adding resistor, I knew 100% it should go down. That's why I was going to agree with Mason. But the way I did the math was wrong. So I knew something's wrong, okay? If you hired me to be an electrical engineer, I'm totally fired. But this number should be 7.2. It needed to be 1.3 ohms. I'll give you the lesson, then I'll tell you what I'm going to do. I'm going to figure out what I did wrong. I'm tempted to figure it out now, but I want to be productive with the time. I'm going to figure it out. I'm going to patch in how I should have done it right, so you can learn from my mistakes. I'm happy to do that. But this is why this is important. If we were to do the Ohm's law, I'm just going to use this space. We have the V, the I, the R. Do it like this. We know the volts, right? 12. And it's going to be 12 divided by the total resistance. That was 4. How many amps did it have with the 2 resistors? 12 divided by 4. 3 amps, right?
3.
And then we went ahead and instead we added another resistor. We thought maybe it'd make the resistance go up, but I knew that was wrong. I just couldn't remember the math well. Instead, we came up with a 1.3. So we did a 12 divided by a 1.3. That one is a funky number. Who knows? 12 divided by 1.3. Anybody want to guess? More amps or less amps?
Less.
Think so? 9.2 amps.
So more.
Exactly.
Yeah.
And so this is I'm totally fine with not being able to do that math, but this is what you have to know. Every circuit you add, even though you're adding resistance in parallel, it's decreasing your total resistance. Your total resistance decreases, your amps goes up, remember? Don't make me show you that picture again. If your resistance goes down, that means ohm is not pulling that hard, there's going to be more amps flowing. We agree on that, right?
Yes.
So you're allowed, even if you have to not remember how to do the math. They do have a calculator, so if you have to do the math, you can cheat on the parallel circuit total resistance calculator, like I did. But you definitely can't get confused and be like, all right, I'm going to add another bulb and that's going to actually decrease the amps. No, it isn't. Definitely not. Not in a parallel. If you add another bulb, I promise you the amperage is going to go up. That's my main takeaway. Let me sit down where it's a little bit quiet and figure out how to do this math, and I'll get it to you, I promise you. Alright? It's probably a fairly simple mistake. I just don't know it right now. Okay. Now, I'll explain to you why we went through all that nonsense. So I gotta get this back. Why do we go through all that? Because again, you have to remember, if you want to add bulbs in a parallel, that's going to increase the amps right here. Because for every parallel branch you add, it lowers the total resistance, which increases the amps right here. That's really where it's important. Extremely. Right, so this one you can see with voltage, they both get 12 volts. This one's going to have 2 amps flowing up here. This one's going to have 1 amp flowing down here. We kind of knew that from before. This is a 12 ohm, this is a 6. Those laws aren't going to change. and that's called Kirchhoff's law. So if you total all the amps of all the branches, that's going to give you the total amps of the actual whole circuit. Cool? 6 plus 4 plus 2, 12. Can't be running a 10 amp circuit on that. Not a 10 amp when you got a 6, a 4, and a 2. You would have to bump that up to probably a 15, and you'd have to run wire appropriate for a 15. Cool. Okay, and then additionally, as part of the law, it tells us any closed loop circuit, the total voltage drop around the loop is equal to the sum of all the voltage drops within the same circuit. What? Okay, let me answer that. If you look, all these volts, let's say we have 12 volts, guaranteed they're all going to drop 12 volts. They're all going to end up with a full 12 volt drop. They all have access to the 12, they're all going to drop 12. That's where it's different than series so much. Cool? Okay, and then, so that's what it's saying, like the whole loop, remember? The voltage drop around the loop is equal to the sum of all voltage drops within the same circuit. And then whenever current passes through any part of the circuit, the inherent resistance present in all conductors and components causes a voltage drop to occur. Say what? If you look at any one of these, when there's current flowing through a circuit, this is going to drop voltage where there's a load. So this is going to drop voltage, this is going to drop voltage, this is going to drop voltage. But this has 12 volts, and this is the only load in this branch. It's going to drop a full 12, going to drop a full 12, going to drop a full 12. So it just functions a little different than a series. Cool. And then like, so for example, if you were to do a, the voltage drop on this, all the voltage drops in the loop, right, would end up equaling 12. Or whatever, I should say, whatever the source is. So if the source is 12, by the time you drop a little here, a little here, a little here, a little here, actually you're going to drop a lot here. It's always going to equal this. What's that number? In this case, we made the total voltage 12 volts. We'd walk up to it with our meter, and we measure it, and it would be 12.00. Then what I can tell you for sure is it's always going to equal 12.00 by the time you do all the drops. So how much did it drop from A to B? Can you tell? It tells you on screen. From here through the fuse to the beginning of the load, it dropped 0.02 volts DC. A little drop. Does that voltage drop make sense? It shouldn't be dropping a lot right here. This is all easy stuff. The load, do you think the load should drop a lot? The load should consume the money, right? We want most of the money going to the son or the daughter of the parent, right? This should get 12 volts, but the truth is, it never gets all 12. There's always a little bit of voltage drop here, a little bit on the switch, probably a little bit on the ground, right? So we dropped 0.025 on basically the supply. We dropped 11.835 on the load. That's pretty good. From C to D, so that's this wire to the ground, we dropped another 0.025. That makes sense. You know, it's dropping just a little bit. It's dropping 2.5 cents. We're paying 2.5 cents just to use this little road right here. Cool. Then on the switch, it actually dropped slightly more. From D to E, from D to E, it dropped 0.06, so we paid 6 cents. Why do you think this is only costing us 2.5 cents and this is costing us 6? That's normal, by the way.
The switch takes more power?
The switch has a little more resistance inside, right? Because it's not a solid wire, it's actually got a metal contactor, so that's going to drop a little more. But like to pay 6 cents to use the bridge, chilling deal. It's a good deal. And then we should drop another about 0.025 on this wire. And the total drop, if you add all these up, you know what it's going to equal?
12.
Exactly 12.00. It always does, it always will. So if you have a battery that's only 9.7 volts, calculate all the voltage drops, it's always going to be 9.76 or whatever the number I said was. Make sense? Now this is going to drop a tiny bit, this is going to drop a lot, but let's focus on this is going to drop a little, this is going to drop a little, this is going to drop slightly more, this is going to drop a little. That means this bulb gets whatever's left over based on, you know, the minimal voltage drops. If you're already starting with a 9, this bulb's going to be dim. You ever seen your lights when your battery's kind of dull, kind of dim, kind of discharged? The lights are dim. Yeah, that's because you have less source voltage. This is not able to produce as much light. It's not able to drop the full 11.835. It's only going to drop like maybe a 9.4. And the amps are going to be very low because the volts are very low. The volts aren't pushing the amp through the wire as much. So that's all normal and predictable. And we will come back to that one. And so this is kind of saying like what I was showing you earlier before. Now that you understand, all these voltage drops will end up equaling the total voltage, the source. So if the source was 12.0 and you're dropping voltage along the way, like we went from 12, we'll make it money. We went from $12 to $11.90. How much did we lose? 10 cents right there. How much did we lose here? 10 cents right here. How much did we lose here though? That's a different number, right? So we dropped a fair amount of voltage here, and then we dropped a fair amount of voltage down here. We dropped 7.1 here. Actually, we didn't drop 7.1. There's 7.1 available. So it had 11.8. It went down to 7.1. That's telling you how much voltage it dropped. What I can guarantee you is if you add all the voltage drops up, it's going to equal whatever you started with.
I figured it out.
You did?
I figured it out.
Think so?
I think so.
You confident?
I don't know how I would be able to explain it.
Well, I'll tell you what. You
No.
hold it. We'll finish this.
Okay.
You and me will work on it.
Okay.
We don't have to because we only have like 15 minutes of the note. Okay, and then here's your current, which I think I actually already showed you. There's your resistance. And then what I wanted to pause at was right here. You will be learning over the next 2 weeks all these different symbols. You got to be able to predict what they do. So like a switch, for example, we talked about this one. What's a switch do?
It turns on or off.
Switches is good. It turns on or off. Yeah, it controls the circuit. So if a switch is open, how much voltage should it drop? It's not touching.
Nothing.
You think it should drop nothing when it's open?
All
of it. Total, yeah. But when it's closed, it should drop just a little, right?
Yeah.
So that's where we're going to build on these, because in the wiring diagram, it's not going to say this switch should drop 12 volts when open and 0.1 when closed. It's not going to say that. You need to know that. So we're going to study each of these symbols, but that's part of, that's actually part of Unit 3 next week. So that's where we get into like this voltage, this tracing, predicting voltage. So you need to know like what the symbols are so you know about how much voltage drop there should be. So when you go to diagnose the car, you're like, hey, I'm dropping 12 volts across that switch when it's closed. That switch is no good. Make sense? So that's kind of where we're going. So with that, I think we're pretty rocking. And when we get into EWD, they're not going to be as simple as that. This is electrical wiring diagram. If you look at this, can you tell what's going on right now?
No.
All right, that's good. So that means I do have a job to do. Teaching you parallel calculation, maybe not. But reading this, maybe so.
So that's actually showing there's
It's
two
like-
switches in there. So
There
when you
is.
Click it back and forth.
It's
the switch
one
is
unit, but the switch does two functions. So if you look at this, what the heck is that? Fuse. This is a connector. These are wires, and it tells you the colors. They go to this switch. If you're in the lock position, this one goes over this way. See how it says lock, right? Then you trace it like, okay, current comes. Right now, nobody's pressing the button, so the current doesn't go anywhere. Don't you make me trace it. No, I'm going to trace it next time, okay? Current's going to go nowhere, but if you put it to the lock, then you got to see 12 volts is going to go through, and it's going to go around through to the motor. The motor is going to consume the 12 and send 0 volts here, and this is going to connect it to ground, and like you got to trace this. Because if the power locks don't work, you need to know where to test and what it should have. So if you can trace it, you can be like, okay, if I press lock, I should have 12 volts here at 1. Then you're going to take your meter and you're going to actually check to see, do I have 12 volts? And if you do, the switch is working. And if you don't, the switch is not working. Make sense? So that's kind of where we're going. But you got to be able to predict the voltages and stuff, so we got to build on a little bit more. Okay, now for my own reference, 1250. We do have slightly a little bit more time. You think you know how to do the math? We could button it up. Got a formula? Come on up. Come on up here.
So,
We probably need that previous picture.
yeah.
Think you got it?
Yes, we're talking about the same one. Okay, so,
Did I make the comment right? Let's see. Cool. Somebody actually made a comment there. I might have had an error. Okay, check it out. Give us the business here.
so resistor 1 was 12, resistor 2 was 6, and resistor 3 was 2, right?
Yeah, 12, 6, and 2.
Okay, so,
Do it right here.
alright,
You can see it, right?
so,
Nice.
on, my bad. No.
Why is it 12? Where's the 12?
Voltage.
Ah, so that might have been an error in the formula.
Yeah.
Sick, dude.
So now, but
Okay.
same thing. So this would be 1. So 1, 2, 6. So now we do 1 plus 2 plus 6, and you would end up getting a total of
This would be 9,
yeah.
and this would be. What the heck is this though? 6, 7.
That'd be
oh,
12.
it's times. 1 times 2
That'd be
times
12.
6, 12, yeah. So 12 over 9. Is that the number that we have?
1.3.
Woo! High five. Figured it out. Alright, so I'm going to run back through just so I make it clear, which makes sense. I was totally tripping, so I need to actually update the formula. So this should be a 12. A 12. In fact, his formula was, hey Bob, we're just going to finish up one thing and then it's all you. We were calculating resistance in parallel and I was totally tripping. I was
Hey,
struggling.
good luck.
You see how often I do it?
Just jump it.
Yeah, that's what I'm power probing. Okay.
Run
Okay.
120 volts through it.
Resistance total equals 12 over, and that first one was 12, you guys got it, right? Times, that second one was 6, you got it, right? And the third one was 2. Okay. And then it was going to be the resistor one is 1 plus 2 plus 6. And I didn't really give myself quite enough room, so I left. You might just make sure I follow me over onto this screen. 12 plus 12, so this is 1 times 12 divided by 6, you guys know is how much? 2 times 12 divided by 2 is 6, and that's over 1 plus 2 is 3, plus 6 is 9. So what's 1 times 2 times 6? We came up with 12. I'm running way over here. Divided by 9 equals 1.3. Okay.
So
Man.
that 1 has to be replaced by the voltage.
Makes sense. So I should really make this formula the voltage, the voltage, the voltage.
True.
Cool. Okay, I didn't catch that. And I also missed that comment. That was actually totally my fault. Okay. But I'm not totally apologizing for that, because like I'm just gonna shoot straight at you. This isn't really what I do on the cars. So forgive me. Okay. You get hit, stop.